Every day the sun rises and gives us light and warmth. It has been in the sky for more than 4.5 billion years, always shining, always burning. But scientists discovered something that changes everything. One day, about 5 billion years from now, the sun will become so big that it will swallow our entire planet. That's right. The same star that gives us life will grow so much that Earth will disappear inside it. How can this happen? What will make the sun grow like that? And the most terrifying part, is there anything that could stop this terrible destiny? Get ready to fall asleep while listening to this video and discover the truth about the future of our planet. Subscribe to the channel. Leave your like and comment from which part of the world you are watching. Get comfortable and relax. Let's begin. Imagine looking up at the sun and thinking it is just a big ball of fire. But it is actually a massive nuclear reactor that has been powering our solar system for billions of years. This reactor, deep within its core, is where the story of life and the eventual fate of Earth begins. The sun is not burning in the way a log in a fireplace does. Instead, it is undergoing nuclear fusion, a process that converts matter into energy on an unimaginable scale. At the heart of the sun, temperatures soar to an incredible 15 million degrees Celsius, a heat so intense that atoms of hydrogen are forced together to form helium. Each fusion reaction releases a tiny amount of energy, but with countless reactions happening every second. The total output is staggering, providing the light and heat that make life on Earth possible. This energy, created in the core, does not rush straight out to space. It embarks on a long and turbulent journey through the sun's layers. Photons, the particles of light, are emitted and absorbed repeatedly, taking thousands of years to travel from the core to the surface. This slow migration is crucial because it acts as a buffer, preventing the sun from collapsing under its own gravity. Gravity is constantly pulling everything inward, trying to compress the star into a smaller space, but the pressure from the fusion reactions pushes outward, creating a stable balance. This equilibrium between gravity and pressure is what keeps the sun in a steady state during its main sequence phase, a period of stability that has lasted for about 4.5 billion years and will continue for several billion more. The fusion process relies on hydrogen as its primary fuel, and the sun has a vast but finite supply. As hydrogen atoms fuse into helium, they leave behind ash that accumulates in the core. This helium ash is denser and does not fuse under the current conditions, so it builds up over time. The continuous fusion gradually depletes the hydrogen in the core, and while there is still plenty in the outer layers, the core itself will eventually run low. When that happens, the balance that has sustained the sun for so long will be disrupted. Without enough hydrogen fusion to counter gravity, the core will start to contract and heat up even more. This contraction increases the temperature and pressure in the core and the surrounding shell of hydrogen, leading to a dramatic increase in fusion rates in those outer layers. The surge in energy production causes the outer layers of the sun to expand outward, beginning its transformation into a red giant. But for now, during this main sequence phase, the sun remains stable, and understanding this nuclear furnace is key to appreciating both its life-giving role and its ultimate destructive potential. The energy generated in the core not only powers the sun, but also dictates the climate and conditions on Earth. Without this constant stream of energy, our planet would be a frozen, lifeless rock. The process of fusion is so efficient that it has allowed the sun to shine consistently for billions of years. But it is not eternal. Every second, the sun converts millions of tons of hydrogen into helium. And while its fuel reserve is enormous, it is not infinite. This gradual consumption means that the sun is slowly changing, even if those changes are imperceptible over human timescales. The physics behind this process were unraveled by scientists in the 20th century, who discovered that stars like the Sun operate on principles of nuclear physics. Fusion occurs when atomic nuclei overcome their mutual electrical repulsion and get close enough for the strong nuclear force to bind them together. In the Sun's core, the extreme temperature and pressure provide the necessary conditions for hydrogen nuclei to collide with enough force to fuse. These collisions result in the creation of helium nuclei, and the mass difference between the initial hydrogen and the resulting helium is converted into energy, as described by Einstein's famous equation. This energy radiates outward, first as gamma rays, which gradually lose energy as they interact with matter, becoming the visible light we see. The journey of a photon from the core to the surface is a random walk, bouncing off electrons and atoms, which is why it takes so long. If photons could travel straight out, the sun would look very different, and its stability would be compromised. The radiative zone, where energy moves primarily by radiation, is followed by the convective zone, where hot plasma rises and cooler plasma sinks, creating circulation patterns that help transport energy to the surface. This entire system is a finely tuned engine, but like all engines, it depends on fuel. The sun began its life with a certain amount of hydrogen, and it has been burning through it steadily. Estimates suggest that the sun has used about half of its core hydrogen, meaning we are roughly halfway through its main sequence lifetime. As the hydrogen depletes, the core contracts, and the outer layers expand slightly, causing the sun to become very gradually brighter over time. This increase in brightness has implications for Earth, as even small changes can affect our climate in the long term. However, the most significant changes will occur when the core hydrogen is nearly exhausted. At that point, the core, now rich in helium, will contract further, heating up until it reaches temperatures where helium itself can start to fuse into carbon. This helium flash will mark a new phase in the sun's evolution. But it is the initial hydrogen depletion that sets the stage for the expansion into a red giant. The expansion will be driven by the increased fusion in the hydrogen shell around the core, which will push the outer layers outward. The sun will swell to many times its current size, potentially engulfing the inner planets, including Earth. But that catastrophic event is still billions of years in the future. For now, the sun continues to fuse hydrogen in its core, maintaining the balance that supports life on our planet. This balance is a testament to the forces of nature, where gravity and nuclear forces are in a delicate dance. Understanding this dance helps us comprehend not only our own star, but also the countless others in the universe. Each star follows a similar life cycle, born from clouds of gas and dust, shining through fusion, and eventually dying when their fuel runs out. The sun is no exception, and its nuclear furnace is both the source of our existence and the instrument of our eventual demise. By studying the sun, we learn about the past and future of our solar system, and we gain insights into the fundamental processes that govern the cosmos. The knowledge that the sun will one day expand and destroy Earth might seem alarming, but it also highlights the precious and temporary nature of our world. It reminds us to appreciate the stable conditions that allow life to thrive and to continue exploring the universe to understand our place within it. The story of the sun's nuclear furnace is a story of power, balance, and change, written in the language of physics and played out over billions of years. It is a story that we are only beginning to understand, thanks to advances in astronomy and nuclear science. As we look up at the sun, we see not just a bright light in the sky, but a dynamic and evolving star, whose inner workings shape our very existence. And while its future expansion is inevitable, that reality is so far off that it does not impact our daily lives. But it does inspire awe and curiosity about the universe. So next time you feel the sun's warmth, remember the incredible nuclear reactions happening deep within, and the delicate balance that makes it all possible. This balance is what allows Earth to be a habitable planet, with liquid water and a stable climate. Without the sun's steady output, life as we know it would not exist. The fusion process is so consistent that it has enabled the development of complex organisms over geological timescales. However, this consistency is temporary, and the very process that sustains us will one day lead to our world's end. But for now, we can study and learn from the sun, using telescopes, satellites, and other instruments to monitor its activity. Scientists measure solar flares, sunspots, and other phenomena to better understand how the sun works and how it affects Earth. This research helps us predict space weather, which can impact satellites, power grids, and communications. It also deepens our knowledge of stellar evolution, allowing us to model the future of the sun with increasing accuracy. These models show that the sun will continue to shine steadily for another 5 billion years or so before it begins its transformation into a red giant. During that time, it will slowly brighten, and Earth will become warmer, but the changes will be gradual. The real turning point comes when the core can no longer support fusion, and the star enters its late stages of life. But that is a story for another time. For now, the focus is on the nuclear furnace that powers our star, a marvel of nature that exemplifies the power of fusion. Fusion is not just the energy source of stars, it is also a potential source of clean energy here on Earth. Researchers are working to replicate the sun's fusion process in laboratories, aiming to harness its power for electricity generation. If successful, fusion energy could provide a nearly limitless and pollution-free power source, echoing the sun's own method. This connection between stellar physics and human innovation shows how understanding the cosmos can lead to practical benefits. So, the sun's nuclear furnace is not only a key to our past and future, but also an inspiration for technological advancement. In summary, the sun is a giant fusion reactor where hydrogen turns into helium, releasing energy that sustains life on Earth. This process is balanced against gravity, creating stability for billions of years. However, the fuel is finite, and eventually, the balance will shift, leading to the sun's expansion and the end of Earth. But that event is so far in the future that it does not diminish the wonder of the sun's current role in our lives. By appreciating the science behind the sun's light and heat, we can better understand our universe and our place within it. This understanding starts with the nuclear furnace at the sun's core, a topic that blends physics, astronomy, and the story of life itself. And as we continue to explore, we uncover more about how stars live and die, enriching our knowledge and inspiring future generations. So, the next time you see the sun, remember the incredible forces at work and the journey that energy takes to reach you. A journey that began thousands of years ago in the heart of a star. This journey is a testament to the interconnectedness of the cosmos, and the sun's nuclear furnace is a perfect example of nature's power and elegance. It is a story that continues to unfold, with each discovery adding a new piece to the puzzle. And while the sun's ultimate fate is sealed, the knowledge we gain from studying it helps us look to the future with both caution and hope. So, let us keep looking up, learning, and marveling at the star that gives us life, even as we understand its eventual death. The sun's steady burning of hydrogen cannot last forever, And the turning point in its life will arrive when the core finally begins to run out of this primary fuel. This moment marks the beginning of the end for Earth, as the star's internal dynamics undergo a dramatic and irreversible shift. For billions of years, the Sun has fused hydrogen into helium in its core, but that process is finite as the hydrogen depletes. The core will start to accumulate what astronomers call helium ash. This helium is denser than hydrogen, and under the current temperature and pressure conditions, it does not undergo fusion itself. So, it just sits there, piling up like the embers of a fire that can no longer burn brightly. Without the outward pressure from hydrogen fusion to counteract the immense force of gravity, the core will no longer be able to support itself. Gravity, always pulling inward, will gain the upper hand, causing the core to contract. This contraction is not a slow, gentle squeeze, but a rapid and violent collapse. As the core compresses, the atoms within are pushed closer together, colliding more frequently and with greater force. This activity generates an enormous amount of heat through a process known as gravitational compression. The temperature of the core will rise dramatically, far beyond its current 15 million degrees Celsius. Paradoxically, this intense heating, caused by the core's collapse, sets the stage for the next act in the solar drama. The heat from the contracting core does not stay confined. It radiates outward, superheating a shell of hydrogen that still surrounds the core. This shell had been relatively dormant, but now, subjected to these skyrocketing temperatures, the hydrogen within it ignites into fusion. This is not the steady, controlled fusion of the core's main sequence life. This is fusion running wild. The hydrogen in the shell begins to fuse into helium at a furiously accelerated rate, like a furnace that has been suddenly cranked to its maximum setting. This shell burning becomes the Sun's new primary energy source, and it is incredibly powerful. The energy produced by this shell fusion creates an immense outward pressure, far greater than what the core ever produced. This radiation pressure pushes violently against the Sun's outer layers, forcing them to expand outward. The star begins to swell, initiating its transformation into a red giant. This expansion is the direct consequence of the fuel exhaustion in the core and the ignition of the shell. It is a fundamental change in the star's structure and energy production. The stable balance between gravity and pressure that define the main sequence is utterly broken. The Sun will never be the same again. This phase is a classic example of stellar evolution, a predictable milestone for stars of the Sun's mass. The entire process, from core hydrogen depletion to the onset of shell burning, happens over a relatively short period in astronomical terms. Perhaps a few 100 million years. While that seems long to us, it is a blink in the lifetime of a star. During this time, the Sun's luminosity will increase significantly as the shell burning intensifies. The increased energy output will have profound effects on the solar system long before the physical expansion fully engulfs the inner planets. For Earth, this means a gradual but relentless increase in incoming solar radiation. The oceans will begin to evaporate, and the atmosphere will become superheated, leading to a runaway greenhouse effect that will ultimately sterilize the planet. But all of that begins with this critical juncture, the moment the core hydrogen is exhausted. It is a point of no return. The accumulation of helium ash is a key part of this process. Helium nuclei require much higher temperatures and pressures to fuse than hydrogen nuclei do in the Sun's core during the main sequence. Those conditions are not met for helium fusion. So, the helium simply accumulates, increasing the core's density. A denser core means a stronger gravitational pull, which accelerates the contraction. It is a feedback loop. Less fusion leads to contraction. which leads to heating, which triggers new fusion elsewhere. The core's contraction continues until it becomes degenerate, a state where matter is so densely packed that quantum mechanical effects dominate. In a degenerate gas, pressure is independent of temperature, which sets the stage for a later, even more violent event, the helium flash. But that comes after this initial red giant expansion triggered by shell hydrogen burning. The shell itself is not a thin, defined layer, but a region where conditions become just right for fusion to reignite. As the core contracts, the temperature in the shell can reach over 100 million degrees Celsius, making hydrogen fusion incredibly efficient and rapid. The energy produced is so vast that it forces the outer layers of the Sun to expand to hundreds of times their current radius. The Sun's surface will cool down during this expansion, changing its colour from yellow to red, hence the name red giant. This cooling of the surface might seem counterintuitive given the increase in total energy output, but it is due to the immense increase in surface area. The energy is spread over a much larger area, so the temperature per unit area drops. Meanwhile, deep inside, the core continues to contract and heat up. The fate of the core and the envelope are now decoupled. One is collapsing while the other is expanding. This is the stellar equivalent of a midlife crisis, a dramatic and fundamental restructuring. The physics behind this is governed by the equations of stellar structure, which describe how pressure, temperature, density, and energy generation vary throughout a star. When the fuel in the core is depleted, the equations demand a new equilibrium, and that new balance involves a larger, cooler envelope and a hotter, denser core. The transition is not smooth. It can be punctuated by instabilities and pulses as the star adjusts to its new energy source. For a star like the Sun, the path to becoming a red giant is well understood from theoretical models and observations of other stars. We see countless red giants in the night sky, each one telling a story of a core that ran out of hydrogen. This process is universal for low to intermediate mass stars. The timing depends on the initial mass of the star. More massive stars burn their fuel much faster and have shorter lives. The Sun, being a relatively average star, will spend roughly 10 billion years on the main sequence before this happens. We are about halfway through that now, so we have another 5 billion years or so until the core hydrogen is depleted. That sounds like a long time, but on a cosmic scale, it is a scheduled appointment. The knowledge of this eventual fate gives us a profound perspective on the temporary nature of our planetary system. The ignition of shell source fusion is a key diagnostic in stellar astrophysics. Astronomers can detect the internal changes in stars by studying their oscillations and brightness variations. The onset of shell burning causes specific changes in a star's pulsations, which can be measured. This allows scientists to determine the evolutionary state of distant stars. For the Sun, we will not be around to observe it directly, but we can learn from other stars. The expansion phase itself will take millions of years, but the initial trigger, the core hydrogen exhaustion, is a relatively swift event. Once the shell burning begins, the Sun's destiny is sealed. The outer layers will become convective, dragging material from the surface down to the burning shell and mixing the products of fusion throughout the star. This can bring elements like lithium to the surface, which would otherwise be destroyed in the hot interior. The composition of the star changes, enriching the outer layers with helium and other elements. This material will eventually be returned to the interstellar medium when the Sun sheds its outer layers entirely later in its life. But for now, during this red giant phase, the Sun will dominate the inner solar system. Its radius will extend well beyond the orbit of Mercury, and it will likely engulf Venus. Earth's orbit may be within the outer fringes of the Sun's atmosphere, leading to intense drag that will cause our planet to spiral inward and be vaporized. The exact timeline for this is complex and depends on how much mass the Sun loses during its expansion. But the process is inevitable. It all traces back to that critical point when the hydrogen fuel in the core is exhausted. This exhaustion is not a sudden event like running out of gas in a car. It is a gradual process where the fusion rate drops as the hydrogen concentration decreases. The core becomes dominated by helium, and fusion becomes less efficient. Eventually, the energy generation cannot support the overlying layers, and the core implodes. This implosion is the catalyst for the entire sequence. The heat from the implosion is what powers the shell burning. So, the death of the core gives birth to a new, more violent phase of fusion in the shell. It is a stellar phoenix, but one that will consume its own planets. Understanding this transition helps astronomers classify stars and understand the chemical evolution of galaxies. The elements created in the core and shell during these phases are scattered into space, providing the raw materials for new stars and planets. Our own solar system formed from the debris of previous generations of stars that went through similar cycles. So, in a way, we are all connected to this process. The Sun's fuel depletion is a reminder of the cyclical nature of the cosmos. For now, though, the Sun remains stable, and we can study these distant futures through models and observations. The key takeaway is that the stability we enjoy is temporary, built on a finite resource. The turning point is built into the very physics of stars, an inevitable outcome of the laws of thermodynamics and nuclear physics. As we look at the Sun, we see an engine in the middle of its long life, but we now know the script for its final chapters begins with the simple act of running out of fuel. This script is written in the language of gravity and fusion, and it is a story that unfolds over timescales that dwarf human history. Yet, by understanding it, we gain a deeper appreciation for the universe and our place within it. The journey from a main sequence star to a red giant is a well-trodden path in the galaxy, and our Sun is no exception. Its fate is shared by countless other stars, each one a testament to the powerful forces that shape the cosmos. So, while the eventual exhaustion of hydrogen in the solar core spells the end for Earth, it is also a natural and essential part of the life cycle of stars, a cycle that creates and destroys, and in doing so, enriches the universe with the elements necessary for life. This makes the study of stellar evolution not just about doom and gloom, but about understanding the origins of everything around us. The iron in our blood, the calcium in our bones, all were forged in stars that lived and died long before our Sun was born. The Sun's own death will one day contribute to future cosmic cycles, but for now, we can observe, learn, and marvel at the processes that govern these celestial giants. The point of fuel exhaustion is not an end, but a transformation, a violent and beautiful change that is as natural as the sunrise. As the Sun's core contracts and the shell of hydrogen around it ignites into furious fusion, the star embarks on the most dramatic transformation in its life, the red giant phase. This is not a gentle swelling, but a catastrophic inflation, where the Sun will bloat to an immense size, fundamentally altering the solar system and sealing the fate of the inner planets. The intense radiation pressure generated by the shell hydrogen burning acts like a powerful force, pushing outward against the star's own gravity. This pressure overwhelms the gravitational pull that has held the Sun together for billions of years, causing its outer layers to expand rapidly into space. The Sun will swell to a diameter hundreds of times larger than its current size. its surface reaching outwards potentially beyond the orbit of Earth. During this expansion, the surface of the Sun will actually cool down, changing its colour from the familiar yellow-white to a deep, ominous red. However, despite this cooler surface, the total energy output, or luminosity, of the Sun increases dramatically because the fusion in the shell is so prodigious. This increase in luminosity is a key point. The Sun becomes vastly brighter, bathing the inner solar system in intense radiation long before its physical surface reaches any planet. The transition into a full-fledged red giant takes millions of years, a relatively short time in stellar terms. The star's outer layers become extremely tenuous and diffuse, more like a vast, hot atmosphere than a solid surface. Convection currents within these layers become dominant, stirring material from deep inside the star and bringing it to the surface. This process can dredge up elements like carbon and oxygen that were forged in the core during earlier phases, enriching the star's outer composition. Meanwhile, the core of the Sun continues its relentless contraction, becoming hotter and denser as it fills with helium ash. The entire structure of the star is now inverted in a way. A small, incredibly dense core is surrounded by a massive, inflated envelope of gas. The physics of this phase are governed by the need for the star to find a new equilibrium after the loss of core hydrogen fusion. The radiation pressure from the shell burning is the primary engine driving the expansion. Photons produced in the fusion reactions carry momentum, and as they bounce around within the stellar material, they exert an outward force. This force is strong enough to push the enormous mass of the Sun's outer layers outward against gravity. The star's envelope becomes so large that its gravitational grip on the outer gases weakens, and the Sun begins to lose mass through a strong stellar wind. This mass loss is a crucial aspect of the red giant phase, as it can affect the star's future evolution and the ultimate extent of its expansion. For the inner planets, the consequences are dire. Mercury will be the first to be engulfed, vaporized almost instantly as the Sun's photosphere expands past its orbit. Venus will likely share a similar fate, its thick atmosphere offering no protection against the stellar inferno. Earth's situation is more complex and depends on the precise details of the Sun's mass loss and expansion rate. Current models suggest that the Sun's radius could extend to about 1 astronomical unit, which is the average distance from the Earth to the Sun. This means Earth could be orbiting within the Sun's outer atmosphere, even if the planet is not completely swallowed. The conditions would be apocalyptic. The drag from the tenuous solar gas would cause Earth's orbit to decay, slowly spiraling it inward to its destruction. The surface of Earth would have already become uninhabitable long before this physical engulfment due to the increased solar luminosity. The oceans would have boiled away. The atmosphere would have been stripped by the intense solar wind, and the surface rocks would melt, creating a global magma ocean. The red giant Sun would dominate the sky, a vast red disk that stretches from horizon to horizon. The process of expansion is not always smooth. Stars can experience thermal pulses where the fusion rate in the shell varies, causing the star to brighten and dim in cycles. These pulses can lead to further mass loss and even the ejection of entire layers of the star. The red giant phase is a temporary but violent stage in stellar evolution. For the Sun, it will last for perhaps 1 billion years or so, a mere fraction of its total lifetime. During this time, the core continues to heat up due to the ongoing contraction. Eventually, the temperature in the core will reach around 100 million degrees Celsius, a threshold where helium nuclei can overcome their mutual repulsion and begin to fuse. This ignition of helium fusion is a sudden and explosive event in a star of the Sun's mass, known as the helium flash. It occurs in the degenerate core. where the pressure is independent of temperature, leading to a runaway thermal reaction. The helium flash releases a tremendous amount of energy in a very short time, but it is mostly contained within the core, helping to lift its degeneracy and establishing a new, stable phase of helium burning. This marks the beginning of a quieter period for the star, where it fuses helium into carbon and oxygen in the core. But the red giant expansion has already set irreversible changes in motion. The Sun may actually shrink slightly during this helium-burning phase, becoming a smaller, hotter star temporarily, but it will later expand again into a red giant for a second time, known as the asymptotic giant branch phase. The entire sequence underscores the dynamic and violent nature of stellar life cycles. The red giant phase is also a key contributor to the chemical enrichment of the galaxy. The strong winds from red giants eject processed material, elements like carbon, nitrogen, and S-process elements into the interstellar medium. This material will eventually form new stars and planets, seeding the cosmos with the building blocks of life. Our own solar system contains elements that were forged in red giants that died long before the Sun was born. So, while the Sun's expansion spells doom for Earth, it is also part of a grand cosmic recycling program. Observing other red giants in our galaxy allows astronomers to study this process in detail. Stars like Betelgeuse in the constellation Orion are famous red giants, and their variability and mass loss provide valuable data for refining stellar models. The study of these stars helps us understand not only the Sun's future, but also the evolution of galaxies. The inflation of the Sun into a red giant is a predictable outcome of well-understood physics, from nuclear fusion to hydrostatic equilibrium. The journey from a main sequence star to a red giant is a standard path for low and intermediate mass stars. The exact timing and details depend on initial mass and composition, but the overall narrative is consistent for humanity, or whatever descendants might exist billions of years from now. This event is an unavoidable natural disaster on a cosmic scale. It serves as a powerful reminder of the impermanence of planetary systems and the dynamic nature of the universe. The knowledge of this future should not be a source of fear, but of wonder and motivation to explore and understand the cosmos while we can. The red giant phase is a testament to the power of stellar processes, where the same forces that give life can also take it away on a scale beyond human comprehension. As we look at the Sun today, it is hard to imagine its serene glow transforming into a monstrous red orb, but the laws of physics demand it. This transformation is already written in the star's internal structure and its finite fuel supply. The catastrophic inflation is the central act in the story of the Sun's death, a dramatic and inevitable unfolding that connects our local star to the vast cycles of stellar birth and death across the universe. Understanding this phase deepens our appreciation for the delicate balance that allows life to exist and the powerful forces that will one day bring that era to a close. The Sun's journey into a red giant is a profound example of cosmic change, a process that is both destructive and creative, ending one world while contributing to the potential for new ones in the distant future. So, while the image of an engorged sun consuming its planets is terrifying, it is a natural part of the life cycle of stars, a cycle that has been repeating for billions of years and will continue for billions more. The red giant phase is not an anomaly. It is a common destiny for stars like our Sun, and by studying it, we learn about the past and future of the cosmos itself. This knowledge connects us to the universe in a fundamental way, highlighting our place in a vast and ever-changing tapestry of stellar evolution. The inflation of the Sun is a slow-motion cataclysm, a a cosmic event that unfolds over timescales incomprehensible to human lives. Yet it is as certain as the laws of nature themselves, and in that certainty there is a strange beauty, a recognition that even stars have lifetimes, with beginnings, middles, and ends. The red giant phase is the beginning of the end for the Sun as we know it, a spectacular and inevitable chapter in the life of our star, after the Sun has inflated into a vast red giant. Its core continues to face an intense internal crisis, contracting relentlessly under the unyielding force of gravity. This core, now composed primarily of helium ash, is in a state known as electron degeneracy, where quantum mechanical effects provide the pressure to support it against collapse. But this state is precarious. The temperature in the core climbs exponentially due to this compression, eventually reaching an astounding 100 million degrees Celsius. At this critical threshold, the helium nuclei, which have been inert until now, finally have enough energy to overcome their mutual electrical repulsion and begin to fuse together. This ignition of helium fusion is not a gentle transition in a star of the Sun's mass. It occurs in a violent and sudden event called the helium flash. The degeneracy pressure in the core means that pressure does not increase with temperature initially, so when fusion starts, it triggers a runaway thermal reaction that releases an enormous amount of energy in a matter of seconds. This flash is so rapid and contained within the core that it does not immediately affect the outer layers of the star. Most of the energy goes into lifting the core out of its degenerate state, making it behave like a normal gas again. After the helium flash, the core stabilizes and begins to fuse helium into carbon and oxygen in a controlled manner, marking the start of a new and relatively stable phase in the star's life. This helium burning phase will last for about 100 million years, a much shorter period compared to the main sequence. During this time, the Sun may actually shrink somewhat from its red giant size and become hotter and more luminous, entering a phase known as the horizontal branch for stars in globular clusters. Though for an isolated star like the Sun, it is simply a period of core helium burning. The energy production now comes from two sources: helium fusion in the core and hydrogen fusion in a shell surrounding the core. This dual shell structure creates a complex internal dynamics. The fusion of helium into carbon occurs through the triple alpha process, where three helium nuclei combine to form a carbon nucleus. This process is highly temperature sensitive, and even small changes can affect the fusion rate. The carbon produced can sometimes fuse with another helium nucleus to form oxygen, enriching the core with these heavier elements. Meanwhile, the hydrogen-burning shell continues to operate, adding more helium to the core, which fuels the ongoing fusion. The stability during this phase is temporary, as the helium in the core is also a finite fuel. As helium is consumed, the core once again begins to accumulate inert carbon and oxygen ash. This sets the stage for another round of core contraction and heating when the helium is depleted. The outer layers of the Sun during this phase are still extensive but less inflated than during the peak red giant stage. The star's luminosity remains high, and its colour may shift to a yellow or orange hue. However, this tranquility is short-lived. Once the core helium is exhausted, the core, now rich in carbon and oxygen, will start to contract again. Since the Sun is not massive enough to reach temperatures high enough to fuse carbon into heavier elements, this contraction does not lead to further fusion ignition. Instead, the core continues to compress into a degenerate state, becoming a white dwarf in the making. The loss of core helium fusion means the star can no longer support itself against gravity in the same way. The hydrogen shell burning reignites with renewed vigor, and the star expands once more into the red giant phase, but this time it is on the asymptotic giant branch, or AGB. This second red giant phase is even more extreme than the first. The star becomes larger and more luminous, and it experiences strong thermal pulses due to instabilities in the helium-burning shell. These pulses cause the star to brighten and dim cyclically and lead to intense mass loss. The Sun will develop a powerful stellar wind, ejecting its outer layers into space at an accelerating rate. This mass loss is crucial because it determines how the star will end its life. The ejected material forms an expanding shell of gas and dust around the star, which is illuminated by the hot core, creating a planetary nebula. The name is a misnomer from early astronomy when these objects looked like planets through telescopes. They have nothing to do with planets. The planetary nebula phase is relatively brief, lasting only tens of thousands of years. During this time, the Sun's core is exposed as a hot, dense white dwarf, with temperatures initially around 100,000 degrees Celsius. This white dwarf is the remnant of the original core, composed mostly of carbon and oxygen, and it will slowly cool over billions of years. The planetary nebula itself will disperse into the interstellar medium, enriching it with elements like carbon, oxygen, and nitrogen that were forged in the star. These elements are essential for life and will one day be incorporated into new stars and planets. For the solar system, the AGB phase and planetary nebula formation mean the complete destruction of the inner planets, if they haven't already been vaporized during the first red giant phase. Any remaining asteroids or comets will be evaporated or ejected. The outer planets might survive, but their atmospheres will be stripped, and they will become barren worlds orbiting a fading white dwarf. The transition from AGB star to planetary nebula involves complex processes, including the ejection of layers in a series of pulses and the shaping of the nebula by binary interactions or magnetic fields. Though for a single star like the Sun, it may be more spherical. The white dwarf that remains is incredibly dense, with a mass about half of the original Sun compressed into a volume the size of Earth. It no longer produces energy through fusion. Instead, it shines due to residual heat, gradually cooling and dimming. The fate of the Earth and the inner solar system is sealed long before this point, during the red giant phases. But the planetary nebula represents the final act in the Sun's life as an active star. This entire sequence, from helium flash to white dwarf, is governed by the initial mass of the star. Stars with higher masses can fuse heavier elements and may end as supernovae. But the Sun's mass dictates this more gradual demise. The study of planetary nebulae and white dwarfs provides astronomers with valuable information about stellar evolution and the chemical enrichment of the galaxy. Many beautiful nebulae, like the Ring Nebula or the Helix Nebula, are examples of this phase in other stars. For the Sun, this future is inevitable, but it is billions of years away. The key takeaway is that the helium flash and subsequent phases are natural steps in the life cycle of a star like the Sun, driven by the relentless laws of physics. The energy produced during these phases comes from nuclear fusion processes that are well understood through models and observations. The transformation from a red giant to a planetary nebula and white dwarf is a common fate for stars of low to intermediate mass, and it plays a vital role in the cosmic cycle of matter. The elements created during the Sun's life and death will someday be part of new celestial bodies, potentially hosting new life forms. So, while the Sun's expansion and eventual demise spell the end for Earth, they also contribute to the ongoing story of the universe, where death and rebirth are intertwined on a galactic scale. Understanding these processes helps us appreciate the fragility of our world and the grandeur of cosmic evolution. The helium flash is a dramatic but hidden event, while the planetary nebula is a visible testament to the star's death throes. Both are essential chapters in the story of the Sun, highlighting the dynamic and ever-changing nature of the cosmos. As we look at the night sky, we see countless stars undergoing similar transformations, each following its own path based on mass and composition. The Sun's journey from a main sequence star to a white dwarf is a reminder of the finite nature of all things, but also of the incredible processes that shape our universe. This knowledge not only satisfies our curiosity, but also deepens our connection to the cosmos, inspiring us to explore and learn more about the forces that govern everything, from the smallest atoms to the largest stars. The phase after the red giant expansion is thus a critical link in the chain of stellar evolution, leading to the beautiful and poignant end represented by a planetary nebula, a fitting farewell for a star that provided light and life for so long. As the magnificent planetary nebula disperses into the depths of space, what remains is the Sun's incredibly dense core, now a white dwarf star. This Earth-sized remnant is composed mostly of carbon and oxygen, packed so tightly that a single teaspoon of its material would weigh many tons here on Earth. Initially, the white dwarf is searingly hot, with surface temperatures reaching up to 100,000 degrees Celsius, shining with a fierce white light. However, with no internal fusion to sustain it, this heat is merely residual, the leftover energy from its earlier life stages. The white dwarf has no energy source and will slowly, inexorably cool down over billions of years. This cooling process is the final chapter in the active life of the Sun, a long, slow fade into darkness. The white dwarf will radiate its heat away into the cold of space, gradually dimming and reddening over time. For the surviving remnants of the solar system, this new era is one of profound change and deepening cold. The outer planets, like Jupiter and Saturn, which may have escaped direct engulfment during the red giant phases, now orbit this faint, diminishing star dot. Their atmospheres, once stripped and altered by the Sun's intense winds and radiation, are now frozen wastelands. Any moons that harboured subsurface oceans, like Europa or Enceladus, will see those oceans freeze solid. The asteroid belt and Kuiper belt objects become even more frigid than they are today. The entire solar system enters a perpetual and deep freeze. The light from the white dwarf, while initially bright, is nothing like the warm, life-giving light of the main sequence Sun. It is a harsh, ultraviolet-rich glow that steadily softens as the dwarf cools. The habitable zone, the region where liquid water could exist, has long since vanished, shrinking to a point virtually at the surface of the white dwarf itself. Any hypothetical observer on a surviving world would see a sky dominated by this small, brilliant point of light, but no warmth would reach them. The orbits of the planets might have changed due to the mass loss the Sun experienced during its red giant and planetary nebula phases. As the Sun shed its outer layers, it lost a significant portion of its mass, weakening its gravitational pull. This causes the remaining planets to spiral outward, their orbits expanding. However, this dynamical change does little to mitigate the deepening cold. The white dwarf era lasts for an astonishingly long time, far longer than the Sun's entire previous existence. While the white dwarf will cool noticeably over the first billion years, it will take many billions more for it to fade significantly. After about 10 billion years, the white dwarf will have cooled to a temperature of a few thousand degrees, appearing as a dim red star. Eventually, after hundreds of billions of years, it will cool further, becoming a black dwarf, a cold, dark stellar remnant that emits no light whatsoever. The concept of a black dwarf is theoretical because the universe is not yet old enough for any white dwarf to have cooled to that state. The universe is only about 13.8 billion years old. So, the Sun's white dwarf will remain a visible, albeit faint, object for time spans that are almost incomprehensible during this entire cooling phase. The internal structure of the white dwarf is supported by electron degeneracy pressure. This is a quantum mechanical effect where electrons are packed so densely that they resist further compression, providing the pressure that prevents the star from collapsing under its own gravity. This pressure is independent of temperature, which is why the white dwarf can maintain its size even as it cools. Its fate is simply to cool down, like a hot ember left in a cold room. There will be no more spectacular events, no flashes or explosions, just a steady and silent dimming. The environment around the white dwarf can be complex. Debris disks made from the shattered remains of asteroids, comets, and perhaps even planets that were perturbed during the chaotic red giant phases might orbit the dwarf. Occasionally, this debris can fall onto the white dwarf's surface, causing accretion and small flashes of light. Astronomers have observed such phenomena in other white dwarf systems, where the stellar atmosphere is polluted by heavy elements from infalling planetary material. This provides evidence that planetary systems can persist in some form long after their star has died, for any life that might have escaped Earth before its destruction and found refuge elsewhere, perhaps on moons of outer planets or in interstellar space. The white dwarf sun would offer little sustenance. The energy output is minuscule compared to the main sequence sun. Concepts for harnessing energy from a white dwarf are purely speculative and would involve technologies far beyond our current imagination, possibly drawing from the star's residual heat or gravitational potential. The galactic context also changes over these vast timescales. The Sun, as a white dwarf, will continue to orbit the centre of the Milky Way galaxy. Over billions of years, the galaxy itself evolves. It may merge with other galaxies, like the impending collision with the Andromeda Galaxy, which is expected to happen in about 4 billion years, well before the Sun becomes a white dwarf. These galactic interactions could gravitationally perturb the solar system, potentially ejecting the white dwarf and its remaining planets into intergalactic space or sending them on new orbits within the merged galaxy. However, the chances of a direct stellar collision are extremely low due to the vast distances between stars. The long-term fate of the white dwarf sun is ultimately to become a cold dot, dark crystal of carbon and oxygen, adrift in the galaxy. It will be a fossil, a relic of a once vibrant star system. The elements that were forged in its core and during its explosive late phases, carbon, oxygen, nitrogen, have been scattered into the interstellar medium by the planetary nebula. These elements will mix with gas and dust clouds, and eventually, billions of years later, they may collapse to form new stars and planets. This is the cosmic cycle of matter. The death of one star provides the ingredients for the birth of others. Our own solar system formed from the debris of previous generations of stars, and the Sun's material will one day be part of new worlds. This perspective highlights the interconnectedness of the universe. The journey of the Sun from a cloud of gas to a white dwarf is a story of transformation on an epic scale for humanity, or any civilization that arises in the far future. The white dwarf sun represents the end of an era. It is a reminder of the impermanence of all things, even stars. Yet, it also underscores the potential for new beginnings elsewhere in the cosmos. The knowledge of this fate can inspire us to appreciate the fragile beauty of our current world and to continue exploring the universe while we have the chance. The study of white dwarfs is an active area of astronomy, helping scientists understand stellar evolution, the age of the galaxy, and the ultimate fate of stars. By analysing the light from white dwarfs, astronomers can determine their composition, temperature, and cooling age. This data helps calibrate models of stellar evolution and provides insights into the history of our galaxy. The Sun's future as a white dwarf is not a unique event but a common destiny for the vast majority of stars in the universe. Understanding this process deepens our appreciation for the physical laws that govern everything from the smallest atoms to the largest cosmic structures. So, while the Sun's light will fade, the story of its material continues, woven into the fabric of new stars, new planets, and perhaps new life. The white dwarf phase is the quiet conclusion to the dramatic story of the Sun, a slow and gentle exit after a long and energetic life. It is a fate that is both humbling and awe-inspiring, reminding us of the vast scales of time and space that shape our universe. As we look up at the night sky, we can see other white dwarfs, and in them, we see the future of our own Sun, a silent testament to the life and death of stars. While the white dwarf Sun represents the final, fading ember of our star's long life, the most dramatic and definitive moment for Earth occurred much earlier, during the Sun's cataclysmic red giant phase. Let's rewind billions of years from that cold, dark future to the pivotal day when the Sun's expansion ultimately reached our world. The process was not sudden. It was a gradual, inexorable encroachment over millions of years. But there was a point of no return. As the Sun swelled, its outer atmosphere, or photosphere, began to brush against Earth's orbit. The planet did not simply fall into the Sun. Instead, it started orbiting within the star's extremely tenuous outer layers. This created immense atmospheric drag, slowly but surely sapping Earth's orbital energy. With each pass, our planet spiraled closer to the solar core, like a satellite decaying in a planet's upper atmosphere. The first noticeable effect was a dramatic increase in solar radiation and stellar wind pressure. The Sun's luminosity had been climbing steadily for millions of years, but now the heat became utterly unbearable. The oceans, which had already been boiling away for some time, would have completely vaporized, creating a thick, steam-filled atmosphere that was quickly stripped away by the intense solar wind. The surface temperature soared to thousands of degrees, hot enough to melt rock and metal. The familiar continents and ocean basins turned into a global magma ocean, a swirling, incandescent sea of molten silicates and iron. The very rocks began to vaporize, adding to the chaotic atmosphere of gaseous rock and metal. The sky, instead of being blue, would have glowed with the intense red light of the Sun's enlarged disk, which now filled a large portion of the sky. Day and night became meaningless as the entire planet was bathed in perpetual, hellish light. The atmospheric drag forces also created tremendous tidal stresses, stretching and compressing the planet. This could have triggered massive global earthquakes and volcanic activity on an unimaginable scale, further churning the molten surface. The Moon, Earth's constant companion, would have shared a similar fate, likely being vaporized or torn apart by tidal forces even before Earth was fully engulfed. The other inner planets had already been consumed. Mercury and Venus were long gone, their material assimilated into the Sun's expanding envelope. The asteroid belt was scoured clean, its objects either vaporized or ejected from the solar system. The outer planets, like Jupiter and Saturn, watched from a distance, their icy moons melting and their atmospheres being violently altered by the increased radiation. The process of engulfment itself was relatively rapid in astronomical terms, but it was not an instant explosion. Earth likely spiraled inward over a period of thousands of years, its material slowly dissolving and mixing into the sun's convective outer layers. The atoms that once made up our planet, the iron from its core, the silicon from its rocks, the oxygen from its water and air were torn apart and became part of the star. These elements were then circulated throughout the sun by convection currents, eventually reaching the surface and being ejected into space later during the planetary nebula phase. This is the ultimate recycling. The material of Earth was returned to the interstellar medium, destined to one day become part of new stars and planets. The timing of this event is based on sophisticated stellar models. The Sun is currently about 4.6 billion years old, and it will spend roughly 10 billion years total on the main sequence. So, in about 5 billion years from now, the core hydrogen will be depleted, triggering the red giant expansion. The actual engulfment of Earth is projected to occur roughly 7.5 billion years from now, during the second red giant phase, known as the asymptotic giant branch. However, Earth will become completely uninhabitable long before that physical engulfment, perhaps in just over 1 billion years, due to the Sun's increasing luminosity during its main sequence evolution. The scenario is not unique to our solar system. Astronomers have observed other stars at various stages of this process. We see red giants like Betelgeuse, which is already in its late stages, and we can study the debris disks around white dwarfs that are polluted with planetary material, direct evidence of such engulfment events. For any hypothetical future civilization, the end would have been foreseen for eons. The gradual brightening of the sun would have been an unavoidable, slow-motion catastrophe. If humanity or its descendants still existed, they would have had to confront this reality. The only long-term survival strategy would have been to leave the solar system entirely and find a new home around a younger star. This presents a monumental challenge for any species, requiring interstellar travel capabilities that are currently beyond our imagination. The knowledge of Earth's ultimate fate casts our present time in a special light. It underscores the fragility and temporary nature of our world, but also its incredible value. The billions of years of stable conditions that allowed life to arise and evolve are a precious and rare gift in the cosmos. Understanding the science behind the sun's evolution helps us appreciate the delicate balance that makes our planet habitable. It also drives scientific inquiry, as we study other stars to refine our models and predict the future of our own. The laws of physics that dictate the sun's life cycle are the same everywhere in the universe, allowing us to learn from distant celestial objects. While the image of Earth being consumed by the sun is terrifying, it is a natural part of the cosmic cycle of matter. The death of one world contributes to the birth of future worlds. The carbon, oxygen, and other elements essential for life were forged in stars that lived and died before the sun was born. Our very existence is indebted to such stellar cataclysms. In a very real sense, we are all stardust, and the material that makes up our bodies will one day be part of something new. This perspective is not meant to incite fear, but to inspire a deeper connection to the universe and a motivation to explore and understand it while we have the opportunity. The day the sun swallows Earth is a definitive end point, but it is also a transformation. The story of our planet does not truly end. Its atoms embark on a new journey across the galaxy. For now, though, the sun shines steadily, and Earth remains a vibrant oasis. We have a responsibility to cherish and protect this world for the time we have. and to continue looking up at the stars with wonder and curiosity, learning all we can about the forces that shape our cosmic home. The certainty of this distant future reminds us that our time is limited, making the present all the more precious. It encourages scientific advancement and the pursuit of knowledge, pushing us to become a spacefaring species capable of surviving beyond our cradle. So, while the final chapter for Earth is written in the laws of physics, the story of humanity, or whatever we may become, is still being written, and its next chapters could span other stars and other worlds, carrying the legacy of life from this pale blue dot into the vast cosmos. After the Earth was consumed and its materials scattered within the Sun's outer layers, the star continued its inevitable evolution towards the planetary nebula phase, a final spectacular display before its long fade into darkness. This transition begins in earnest during the asymptotic giant branch stage, where the Sun's internal structure becomes increasingly unstable. The core is now a dense sphere of carbon and oxygen, incapable of further fusion, surrounded by a shell where helium burns violently into carbon and an outer shell where hydrogen fuses into helium. These layered fusion processes are not steady. They undergo thermal pulses, sudden bursts of energy that cause the star to brighten dramatically and eject large amounts of material into space. The mechanism behind this mass loss involves a combination of radiation pressure and powerful stellar winds. As the star pulsates, its outer layers become loosely bound, and the intense light from the core pushes on dust grains that form in the cooler outer atmosphere. These dust grains, acting like tiny sails, drag the surrounding gas outward, accelerating it away from the star over thousands of years. This continuous ejection strips away the Sun's envelope, exposing the incredibly hot core. Once the core is laid bare, its surface temperature skyrockets to over 100,000 degrees Celsius, and it begins emitting copious amounts of ultraviolet radiation. This UV light floods the surrounding ejected gas, ionizing atoms by stripping away electrons. When these electrons eventually recombine with ions, they emit light at specific wavelengths, causing the gas to glow in vibrant colours. This illuminated, expanding shell of gas is what we observe as a planetary nebula. The name is a historical artifact from the 18th century when astronomers like William Herschel noted their planet-like round appearance through telescopes. They have no actual connection to planets. The morphology of planetary nebulae can vary widely, from simple spherical shells to complex bipolar or butterfly shapes, often influenced by binary companions, magnetic fields, or the star's rotation. For a single star like the Sun, the nebula might be roughly spherical, but it could still exhibit asymmetries due to uneven mass loss or rotation. The expansion velocity of the nebula typically ranges from 10 to 30 kilometers per second, and it can grow to several light years across over its lifetime. This phase is remarkably brief in astronomical terms, lasting only about 20,000 to 50,000 years before the nebula disperses into the interstellar medium. During this time, the central star, now revealed as a white dwarf, shines intensely due to its residual heat. The white dwarf is the remnant core, with a mass roughly half that of the original Sun compressed into a volume no larger than Earth. It is supported against gravitational collapse by electron degeneracy pressure, a quantum effect where densely packed electrons resist further compression. With no internal fusion, the white dwarf's only energy source is the heat left from its previous life, and it will slowly cool over billions of years. The planetary nebula phase is crucial for the chemical enrichment of the galaxy. The ejected material is laden with heavy elements synthesized during the star's life, including carbon, oxygen, nitrogen, and S-process elements like strontium and barium. These elements are forged in the stellar interior through processes like the triple alpha reaction for carbon and the CNO cycle for nitrogen, and they are brought to the surface by deep convection currents during the red giant phases. When ejected, they seed the interstellar medium, providing the raw materials for new generations of stars, planets, and potentially life. In fact, the carbon-based molecules essential for biology on Earth originated from such stellar explosions. Observations of planetary nebulae offer astronomers a wealth of information. By analysing their spectra, we can determine the chemical composition, density, temperature, and expansion dynamics of the ejected gas. These data help refine models of stellar evolution, particularly for the late stages of low and intermediate mass stars. Planetary nebulae also serve as distance indicators in cosmology, though their use requires careful calibration due to variations in their properties. The study of these objects has revealed that their shapes are often shaped by interactions with binary stars or by magnetic fields, leading to intricate structures like jets, rings, and lobes. For the solar system, the planetary nebula phase marks the ultimate dissolution of the former planetary system. Any surviving outer planets, like Jupiter or Saturn, would be bathed in the nebula's intense radiation and subjected to the outflowing gas. Their atmospheres would undergo further erosion, and any remaining moons or ring systems could be stripped away or vaporized. Debris disks around white dwarfs, detected through infrared excess or spectral pollution, indicate that asteroid and comet belts can persist after the star's death, with material occasionally falling onto the white dwarf's surface. This accretion can cause observable signatures, such as metal lines in the white dwarf's spectrum, providing direct evidence of the ongoing dynamical evolution of planetary systems post-main sequence. The Sun's planetary nebula will be a visible object from elsewhere in the galaxy, a glowing testament to its former glory. From within, however, the environment would be hostile, with high-energy radiation and expanding gas creating conditions unsuitable for life. The beauty captured in images from space telescopes contrasts with the destructive forces at play. Understanding this phase deepens our appreciation of the cosmic cycle of matter and energy. It underscores the transient nature of stellar existence and the interconnectedness of all cosmic phenomena. The knowledge that the Sun will one day undergo this transformation encourages ongoing astronomical research and technological advancement. As we seek to unravel the details of stellar death and its implications for the galaxy, while the planetary nebula represents the end of the Sun's active life, it is also a beginning, as its ejected material will eventually coalesce into new stars and planets, continuing the endless cycle of birth and death in the universe. This perspective not only fuels scientific curiosity, but also inspires a sense of wonder about our place in the cosmos, motivating us to protect and cherish our world while we have it. After the planetary nebula has faded and dispersed, the white dwarf Sun is left alone in space, a dense Earth-sized remnant of what was once a vibrant star. This white dwarf is incredibly hot initially, with surface temperatures soaring to around 100,000 degrees Celsius, but it has no internal fusion to sustain that heat. It begins a slow and relentless cooling process, radiating away its residual thermal energy into the cold vacuum of space. This cooling is the final act in the solar life cycle, a gradual fading that stretches over timescales almost impossible to comprehend. The white dwarf is composed mostly of carbon and oxygen, packed so densely that quantum mechanics, specifically electron degeneracy pressure, prevents it from collapsing further. This pressure is independent of temperature, meaning the dwarf maintains its size even as it cools. Unlike a normal star, which would contract, the cooling curve is steep at first. The white dwarf loses heat rapidly because it is so hot and small, with a high surface area to volume ratio. Over the first billion years, its temperature might drop to 20,000 degrees, and its colour shifts from brilliant white to yellow, then to red. As it cools, its luminosity decreases dramatically. From its initial intense glow, it dims to the brightness of a full moon, then to that of a bright star, and eventually it becomes faint and hard to detect. The rate of cooling slows down over time because as the dwarf gets cooler, it has less heat to radiate per unit time. After about 10 billion years, the white dwarf sun might have cooled to a temperature of a few thousand degrees, appearing as a dim red ember in the sky. The concept of a black dwarf comes into play here, a theoretical state where the white dwarf has cooled to the background temperature of the universe, around a few degrees above absolute zero, and emits no detectable light. However, the universe is only about 13.8 billion years old, so no white dwarf has had enough time to cool to a black dwarf yet. The sun's white dwarf will take many times the current age of the universe to reach that state. During this immense cooling period, the environment around the white dwarf is bleak. Any remaining planets, like Jupiter or Saturn, orbit in perpetual darkness and cold. Their surfaces and atmospheres are frozen solid, with no warmth from the star to sustain any processes. The orbits of these planets may have expanded due to the mass loss during the red giant and planetary nebula phases. But this offers no comfort as the energy source is gone. The solar system becomes a ghost town, with the white dwarf as a fading tombstone. The physics of white dwarf cooling is well studied through observations of other white dwarfs in our galaxy. Astronomers use colour and brightness measurements to estimate their temperatures and ages, helping to calibrate cosmic clocks. The cooling process depends on the composition of the white dwarf. Impurities or crystallization of the carbon-oxygen core can release latent heat, slightly slowing the cooling. In fact, after billions of years, the interior of the white dwarf may begin to crystallize, forming a giant diamond-like structure. But this happens deep inside and doesn't affect the external cooling significantly. The surface of the white dwarf is composed of lighter elements like hydrogen or helium, if any remain, but often accretion of interstellar material or debris from disrupted planets can pollute the atmosphere, causing spectral lines that reveal its composition. For the solar system, this long fade means the end of light and heat as we know it. No. The white dwarf sun will no longer support any habitable zone. The region where liquid water could exist shrinks to nothing. Any hypothetical life that might have escaped to outer planets or moons would face absolute zero temperatures and no energy source. The galaxy continues to evolve around this cold remnant. The Milky Way will merge with other galaxies, like Andromeda, in about 4 billion years. But that event will happen long before the sun becomes a white dwarf. Over the eons, gravitational interactions with passing stars or molecular clouds could perturb the orbits of the white dwarf and its remaining planets, possibly ejecting them into interstellar space. The chance of a direct collision is minuscule due to the vast distances between stars. The white dwarf sun will orbit the galactic center for billions of years, slowly cooling and dimming. As it cools, its spectrum shifts towards the infrared, and eventually, it emits no visible light at all. The end of light is not a sudden event, but a gradual dissipation. After 100 billion years, the white dwarf might be detectable only through its infrared emission or gravitational influence. In the far future, beyond trillions of years, the white dwarf could become a black dwarf, completely invisible and dark, This ultimate fate is shared by most stars in the universe, as over 90% of stars end as white dwarfs. The material that once made up the Sun and Earth is now locked in this cold, dense object, but it's not entirely gone from the cosmic cycle. However, in the absence of any external process, the white dwarf will remain as is, slowly cooling towards absolute zero. The study of white dwarf cooling helps scientists understand the age of the galaxy and the universe. By looking at the coolest white dwarfs in star clusters, astronomers can estimate their ages, providing a lower limit for the age of the galaxy. This connects to broader cosmological questions. For humanity, the knowledge of this future highlights the impermanence of stars and the importance of our current era of cosmic light. While the sun's light will fade, the elements it produced are now part of the interstellar medium, thanks to the planetary nebula, and will seed new stars and planets. But for the solar system, the cooling white dwarf marks the end of an era. The silence and darkness that follow are a stark contrast to the vibrant, life-giving star that once shone. In a way, this cooling process is a peaceful conclusion to the violent phases of stellar death. There are no more explosions or expansions, just a slow, quiet fade. The laws of thermodynamics dictate this outcome. Heat always flows from hotter to cooler objects until equilibrium is reached. The white dwarf sun is no exception. As we observe other white dwarfs today, we see snapshots of this future. Stars like Sirius B, the white dwarf companion to Sirius, show us what the sun will become, hot and dense now, but destined to cool. Understanding this process deepens our appreciation for the timescales involved in cosmic evolution. It also puts our own existence into perspective. We live in a brief window of stellar stability, between the formation of the sun and its eventual cold death. This knowledge can inspire us to make the most of our time, to explore the universe, and to seek out other worlds around younger stars. The cooling of the white dwarf is the final footnote in the story of the sun, a story that began with a collapsing cloud of gas and dust. From that birth, through its main sequence life, its red giant expansion, the planetary nebula, and now the long cooling, the sun follows a path dictated by physics. And as it fades, it reminds us that even stars have lifetimes, and that the cosmos is in a constant state of change, with beginnings and endings on scales beyond human imagination. So, while the light of the sun will one day go out, the legacy of its material continues, and our understanding of it enriches our view of the universe. As the white dwarf sun continues its slow fade into darkness, its story is far from over in a cosmic sense, because the material it ejected during its life and death now begins a new journey, enriching the galaxy with the essential elements for future stars and planets. This chemical legacy is perhaps the most enduring part of the sun's existence, transforming its death into a contribution for new life elsewhere. When the sun was in its red giant and planetary nebula phases, it expelled vast amounts of gas and dust into space, carrying with it elements that were forged in its core and shells. These elements include carbon, oxygen, nitrogen, and trace amounts of heavier metals, all spread into the interstellar medium. This process is not unique to the sun. It is a fundamental aspect of stellar evolution that drives the chemical enrichment of the entire universe. The interstellar medium is like a cosmic recycling bin, filled with gas and dust from countless stellar explosions and ejections. Over time, gravity pulls these materials together into dense clouds, which can collapse to form new stars and planetary systems. The sun itself was born from such a cloud that contained elements from previous generations of stars. So in a very real way, we are all made of stardust, the carbon in our bodies, the oxygen we breathe, and the iron in our blood were all created in stars that lived and died long before the sun ignited. Now, the sun is returning the favour, contributing its own processed material back into the galactic ecosystem. This cycle ensures that the universe becomes increasingly enriched with heavy elements over time, making it possible for rocky planets like Earth to form and for life to emerge. The elements ejected by the sun are particularly important because they include key ingredients for organic chemistry. Carbon, for instance, is the backbone of life as we know it, forming complex molecules like proteins and DNA. Oxygen is crucial for water and respiration, while nitrogen is a component of amino acids and nucleotides. Without these elements being scattered by stars like the sun, the universe would consist mostly of hydrogen and helium, with no planets or life. The planetary nebula phase was especially effective at dispersing these elements because the intense ultraviolet radiation from the hot white dwarf core ionized the gas, making it expand rapidly and mix with surrounding interstellar material. This mixing process can take millions of years, but eventually, the sun's remnants become part of a larger molecular cloud. When such a cloud collapses under gravity, it fragments into clumps that form new stars. These new stars will have a higher metallicity, a term astronomers use for elements heavier than helium than the sun did at its birth, meaning they are more likely to have planetary systems with diverse compositions. Some of these planets could be Earth-like, with conditions suitable for life. Thanks in part to the sun's contribution, the study of stellar nucleosynthesis explains how these elements are created. During its main sequence life, the sun fused hydrogen into helium in its core. Later, in the red giant phase, helium was fused into carbon and oxygen through the triple alpha process. In more massive stars, even heavier elements like iron are produced. But for a star like the sun, carbon and oxygen are the primary products. Additionally, processes like the S process slow neutron capture during the asymptotic giant branch phase can create elements like strontium, barium, and technetium, which are also ejected. These elements are detected in the spectra of planetary nebulae and in the atmospheres of older stars, providing evidence for this enrichment. Observations of other planetary nebulae, such as the Ring Nebula or the Helix Nebula, show abundant carbon, oxygen, and nitrogen, confirming that stars like the sun are factories for these elements. The dispersal of these materials is aided by galactic dynamics. The sun orbits the Milky Way, and as it does, its ejected material gets swept up in spiral arms or mixed with other clouds through supernova shocks and stellar winds. Over billions of years, this material becomes uniformly distributed throughout the galaxy, though local enhancements can occur in star-forming regions. The sun's specific contribution might seem small on a galactic scale, but combined with countless other stars, it plays a vital role in increasing the overall metallicity of the universe. This has implications for the future of galaxy evolution. As more heavy elements become available, the formation of planets becomes more common, and the potential for life increases. In the far future, new solar systems will form from clouds that include the sun's recycled atoms, perhaps on some distant world. These atoms will become part of oceans, mountains, or even living organisms, carrying forward the legacy of our star. This idea connects us to the cosmos in a profound way. The same atoms that once made up the Earth or were fused in the sun could one day be part of an alien civilization. For scientists, tracing the chemical evolution of the galaxy is a key area of research. by analysing the compositions of stars of different ages. Astronomers can reconstruct the history of element production. Young, metal-rich stars tell us about recent enrichment, while old, metal-poor stars reveal conditions in the early universe. The Sun is a typical middle-aged star with average metallicity, so its life cycle serves as a benchmark for understanding how typical stars contribute to galactic chemistry. Moreover, the study of white dwarfs themselves provides clues. When they accrete material from debris disks, their atmospheres show pollution from rocky bodies, indicating that planetary systems can survive stellar death and that elements are being recycled locally. The long-term fate of the Sun's material depends on the evolution of the galaxy. The Milky Way is on a collision course with the Andromeda Galaxy, and in about 4 billion years, they will merge, triggering a burst of star formation. During this merger, the Sun's ejected elements could be incorporated into new stars in the resulting galaxy, on even longer timescales. As the universe expands and stars die, the concentration of heavy elements will continue to rise, though the rate of star formation will eventually decline. In the very distant future, after all stars have burned out, the universe will be filled with stellar remnants and dispersed elements. But the chemical legacy of stars like the Sun will endure for humanity. This perspective highlights the interconnectedness of all things. It encourages a sense of stewardship for our planet, as we are temporary custodians of atoms that have travelled through cosmic time. It also inspires exploration and curiosity about other worlds that might be forming from the same stellar debris. While the Sun's light will fade, its material lives on, participating in the endless cycle of birth, death, and rebirth that defines the cosmos. This cycle is driven by fundamental forces like gravity and nuclear physics, and understanding it helps us appreciate our place in the universe. So, as we look up at the night sky, we can see not just stars, but potential futures where the Sun's legacy continues to shine in new forms. The chemical enrichment process is a testament to the dynamic and creative nature of the universe, where even in death, there is life and possibility. This knowledge transforms the narrative of the Sun from a single star's life story into a chapter in the grand saga of cosmic evolution, reminding us that we are part of something much larger than ourselves. The journey of the Sun's material is just one thread in the vast tapestry of cosmic evolution, a process that unfolds on scales far grander than a single star's life cycle. To fully appreciate the Sun's fate, we must zoom out and see it within the context of the entire universe's timeline and the ultimate destinies of all celestial objects. The universe itself is approximately 13.8 billion years old, and our Sun is a relative newcomer, having formed only about 4.6 billion years ago. This means the cosmos was already 9 billion years old when our solar system came into being. Plenty of time for multiple generations of stars to have lived, died, and seeded space with heavy elements. The Sun's life, from its birth in a nebula to its death as a white dwarf, follows a predictable path for a star of its mass. But it is just one of countless billions of similar stories playing out across the galaxy. The future of the universe, however, holds changes that will dwarf the Sun's personal story. In about 4 billion years, the Milky Way galaxy is expected to collide and merge with the Andromeda Galaxy. This event will happen while the Sun is still on the main sequence, though it will be a red giant by the time the merger is complete. During this galactic collision, the Sun and its planetary system could be flung into a new orbit within the resulting elliptical galaxy, nicknamed Milkomeda. The chances of stars physically colliding are extremely low due to the immense distances between them. but the gravitational upheaval will reshape the entire galactic structure. As the eons pass, star formation will gradually decline as the interstellar gas is used up and not replenished. The universe continues to expand at an accelerating rate, driven by the mysterious force known as dark energy, over trillions of years. This expansion will have profound consequences. Other galaxies, beyond our local group, will be pushed away by the expanding space, their light red-shifting until they are no longer detectable. The universe will become a much lonelier place from our perspective. Within our galaxy, stars will continue to age and die. The most massive stars will end their lives in spectacular supernova explosions, forging even heavier elements and leaving behind neutron stars or black holes. Low-mass stars, like red dwarfs, will burn for trillions of years, far outliving the sun's white dwarf remnant. But eventually, even these long-lived stars will exhaust their fuel. The universe will enter a degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. The white dwarf sun will still be cooling during this time, but it will be one among countless others. The planets that may still orbit it will be cold and dark, their atomic activity slowed to a near standstill by the extreme cold, on timescales of quadrillions of years. Even these remnants face further evolution. White dwarfs may undergo physical collisions in the dense cores of star clusters, potentially triggering supernova. But for an isolated star like the Sun, this is unlikely. A more probable fate is the gradual decay of orbits due to gravitational radiation over incredible time spans. The planet's orbits around the white dwarf will decay, and they will spiral inward. However, this process is so slow that the universe may not yet be old enough for it to have happened to any planetary system. Another theoretical process is proton decay, if it exists, where the fundamental matter in white dwarfs and neutron stars slowly evaporates over perhaps 10 to the power of 34 years. If protons do not decay, the fate of these objects is to eventually be ejected from galaxies or accreted by black holes. The galaxy itself will evolve dynamically through a process called relaxation. Gravitational interactions between stars and remnants will cause some to be ejected into intergalactic space, while others will sink towards the centre, potentially being swallowed by the supermassive black hole. The Sun's white dwarf could share either of these fates over these immense periods. The final state of the universe, according to our current understanding, is the heat death. In this scenario, the universe reaches a state of maximum entropy, where no energy is available to do work. All matter is either in black holes or is spread out as a thin, cold soup of particles and radiation. The temperature approaches absolute zero universally. Black holes themselves are not eternal. They slowly lose mass through Hawking radiation. A black hole with the mass of the Sun would take an unimaginable 10 to the power of 67 years to evaporate. The supermassive black holes at galactic centres would take even longer, after the last black hole evaporates. The universe would contain only photons and leptons, spread infinitely thin and unable to form any new structures. This is the ultimate cosmic context for the Sun's story. Its birth, life, and death are a vibrant but fleeting episode in the early, active phase of the universe. The era of stars is finite. We live in a privileged time when the universe is alive with light and energy, able to support complex chemistry and life. The Sun's journey from a shining star to a cold remnant is a microcosm of the universe's own journey from the hot Big Bang to the cold, dark future. Understanding this broad context gives profound meaning to the study of stellar evolution. It connects the physics of a single star to the largest questions in cosmology. The laws that govern the sun's fusion are the same laws that govern the expansion of the universe. This continuity is a powerful reminder of the unity of physics for humanity. This knowledge is both humbling and inspiring. It tells us that our time, and the time of our star, is limited, but it also places us at a cosmic crossroads. We exist at a time when we can observe and understand these processes, from the nuclear furnaces in stars to the fate of the cosmos. This ability to comprehend the universe is perhaps as remarkable as the cosmic story itself. The sun's fate is sealed, but the human story of exploration and discovery is still being written. By looking outward, we learn not only about the stars, but also about our own place in this grand narrative. The light from the sun that now warms our planet will one day be gone, but the knowledge we gain from studying it will remain. A testament to a species that looked up at the sky and sought to understand its home in the cosmos. So, while the cosmic context ends in cold and darkness, our present is filled with light and the incredible opportunity to learn, a fleeting but precious moment in the vast timeline of the universe. While the grand cosmic timeline stretches toward an unimaginably distant future, our understanding of the sun's fate is not mere speculation. It is a robust scientific conclusion built upon precise methods and observations that allow us to decipher the life stories of stars. The science behind these predictions is a fascinating detective story, one that relies on our ability to study countless other stars at different stages of their lives. Imagine having a photo album of 1 million people, each picture taken at a different age. By compiling these images, you could reconstruct the entire life cycle of a human from infancy to old age. Astronomers do the same with stars, using powerful telescopes to gather light from millions of stars across the Milky Way and beyond. The primary tool in this cosmic investigation is spectroscopy, the art of dissecting starlight. When light from a star passes through a spectrograph, it spreads out into a rainbow-like spectrum, crossed by dark and bright lines. These lines are the fingerprints of chemical elements, revealing the star's composition, temperature, density, dot, and even its motion through space. By analysing the spectrum of a star, we can determine what it is made of and how hot it is, which are fundamental clues to its mass and age. For instance, the strength of hydrogen lines tells us about the star's surface temperature, while the presence of certain metals indicates its overall composition and generation. This allows us to classify stars, sorting them into categories like the main sequence, red giants, and white dwarfs, creating a comprehensive picture of stellar evolution. Another crucial method involves studying star clusters. Clusters are gold mines for astronomers because all the stars in a single cluster formed from the same giant cloud of gas and dust at roughly the same time. This means they all have the same age and initial chemical composition, but they have different masses. By observing a cluster like the Pleiades, which is young, we see many bright, blue dot, massive stars still on the main sequence. In an older cluster, like a globular cluster, the massive stars have already evolved off the main sequence and become red giants or white dwarfs. By plotting all the stars in a cluster on a Hertzsprung-Russell diagram, which graphs luminosity against temperature, we see a clear pattern that traces out the path of stellar evolution. The point where stars begin to turn off the main sequence tells us the cluster's age. This direct observational evidence confirms the theoretical models that predict how long a star of a given mass will spend fusing hydrogen. For the Sun specifically, dot, we have more direct ways to probe its interior. Helioseismology is the study of sound waves that ripple through the Sun. By carefully observing the Sun's surface oscillations, Much like geologists study seismic waves to understand Earth's interior, scientists can infer the sun's internal structure, density, and temperature. These data have beautifully confirmed our models of the solar interior, including the size of the core where fusion occurs. We also directly sample the solar wind with spacecraft and study solar neutrinos, elusive particles produced in the core's fusion reactions. Detecting these neutrinos confirms that nuclear fusion is actively powering the sun right now. Furthermore, we can observe stars that are currently going through phases the sun will experience in the future. We see red giants like Arcturus and Mira, whose vast sizes and strong stellar winds show us what the sun will become. We observe planetary nebulae like the Ring Nebula, with their glowing gas and central white dwarfs, illustrating the fate of the sun's envelope and core. And we have identified thousands of white dwarfs, allowing us to study their cooling processes and compositions. These observations are coupled with sophisticated computer modeling. Physicists write equations based on the fundamental laws of physics, gravity, thermodynamics, hydrodynamics, and nuclear physics to create simulations of stellar interiors. These models calculate how pressure dot, temperature, and density change from the core to the surface, and how the star evolves as its fuel is consumed. The models predict that a star with the sun's mass will spend about 10 billion years on the main sequence, then expand into a red giant, and finally end as a white dwarf. The fact that these models successfully explain the properties of the vast majority of stars we observe gives us tremendous confidence in their predictions. The timing of Earth's demise is also derived from these models, which calculate how the sun's luminosity and radius will increase over time. We can even test our models on stars that are similar to the sun but older, confirming that their properties match what we would expect. This multi-pronged approach, spectroscopy, cluster studies, solar studies, direct observation of stellar life stages, and computer modeling forms a consistent and powerful scientific narrative. It is a story built on evidence, not guesswork. This is how we know, with a high degree of certainty, the future that awaits our star and our planet. The process is continually refined as our telescopes become more powerful and our computers more capable, allowing for ever more detailed and accurate simulations. This scientific journey demonstrates the power of human curiosity and reason to unravel the mysteries of the cosmos, to look at the present state of the universe and deduce its past and future. It connects the light from a distant star to the equations on a physicist's blackboard, revealing a universe that is comprehensible and governed by consistent laws. This understanding is a remarkable achievement, allowing us to see billions of years into the future and comprehend the life cycle of the very star that gives us life. So, when we talk about the sun engulfing the Earth, it is not a fantastical myth. It is a forecast based on the same rigorous principles that allow us to predict the weather or send a spacecraft to Mars. The methods may be complex, involving quantum mechanics and general relativity, but the underlying logic is straightforward. Observe, model, dot, test, and predict. This is the scientific method applied on a cosmic scale, and it provides us with the most reliable picture we can have of the distant future. It transforms the sun from a silent, unchanging orb in the sky into a dynamic, evolving entity with a birth, a life, and a death, whose story we are privileged to be able to read in the light it sends our way. This knowledge empowers us, giving us a true perspective on our place in space and time, and inspiring us to continue exploring and learning about the incredible universe we inhabit. The science behind the prediction is as beautiful and compelling as the cosmic story it reveals. a testament to our species' relentless drive to understand the world around us, from the smallest atom to the largest star. The scientific narrative of the sun's expansion is not just a distant prediction. It is a process that has already begun, unfolding with a slow, inexorable certainty that will fundamentally transform the solar system long before the final cataclysm. The sun is not a static object. It is a dynamic star undergoing constant change, and the early stages of its evolution into a red giant are already encoded in its present behavior. The most significant and measurable change is the gradual increase in the sun's luminosity. Since its birth approximately 4.6 billion years ago, the sun's brightness has grown by about 30%. This increase is a direct consequence of the changing composition in its core. As hydrogen fuses into helium, the core becomes denser and hotter, which in turn makes the nuclear fusion reactions proceed more efficiently. This causes a slow but steady rise in energy output. This trend is not speculative. It is a fundamental prediction of stellar model simulations that have been rigorously tested against observations of other stars. For Earth, this increasing solar luminosity has profound implications for the long-term future of our climate and biosphere. In roughly 600 million to 1 billion years from now, the increased solar energy will trigger a runaway greenhouse effect. The higher temperatures will lead to increased evaporation of seawater, and water vapor is a potent greenhouse gas. This will trap more heat, further raising temperatures in a feedback loop that will eventually cause the oceans to boil. The carbonate-silicate cycle, which currently helps regulate Earth's temperature over geological timescales, will be overwhelmed. The atmosphere will become saturated with water vapor, and the surface temperature will rise to hundreds of degrees, making the planet uninhabitable for all known life. This is the first act of the solar endgame, and it will occur while the sun is still securely in its main sequence phase, billions of years before the physical expansion begins. The timeline for this is based on sophisticated climate models coupled with the well-understood stellar evolution models. After the oceans boil away, the planet will become a scorching, high-pressure desert. The intense ultraviolet radiation from the brighter sun will break apart water molecules in the upper atmosphere, and the lightweight hydrogen will escape into space, leading to the permanent loss of Earth's water. The surface will melt into a global magma ocean, erasing all geological features and effectively sterilizing the planet. Meanwhile, the sun continues its internal transformation. The helium ash accumulating in the core continues to increase its density, forcing the core to contract and heat up further. This gradual process is the prelude to the main fuel crisis. The rate of luminosity increase will accelerate as the sun approaches the end of its main sequence life, about 5 billion years from now. The core will have exhausted its hydrogen fuel, marking the end of the stable phase and the beginning of the rapid and dramatic red giant transition. The current changes, while slow, are the foundational steps leading to that event. We can observe this process in other stars. By studying solar analogues, stars very similar to the Sun in mass and composition at various ages, astronomers see a clear correlation between a star's age and its luminosity. Middle-aged stars like the Sun are consistently brighter than their younger counterparts, confirming the models. This observational evidence solidifies our understanding that the Sun's evolution is a continuous process, not a series of disconnected events. The changes are already happening. We just cannot perceive them on a human timescale. The framework for the future destruction of Earth is being built today, atom by atom, in the Sun's core. Every fusion reaction not only provides light and heat, but also brings the star one step closer to its eventual transformation. This perspective transforms our view of the Sun from a permanent fixture to an evolving entity with a life story that is already in its middle chapters. The increasing solar output also has implications for the other planets. Mars, already a cold desert, may temporarily experience a warmer period, but it lacks the magnetic field and atmosphere to become a true refuge. Venus will become even more hellish. The outer planets will see their icy moons melt, potentially creating temporary subsurface oceans on worlds like Europa. But these will be short-lived as the Sun's expansion continues. The early stages of the Sun's death are thus a reminder of the dynamic nature of planetary climates and the delicate balance required for habitability, for humanity, or whatever intelligent life exists in the distant future. This slow-motion crisis presents a daunting challenge. The timescales are long, but the outcome is certain. It underscores the necessity of becoming a spacefaring civilization, capable of migrating to other star systems, as a long-term survival strategy. The knowledge that the Sun is already changing, that the clock is ticking, adds a layer of urgency to the human project of exploration and discovery. It is a call to look beyond our cradle and establish a presence elsewhere in the galaxy. The science that tells us this story is the same science that could provide the means to escape it. So, while the final engulfment is billions of years away, the process that leads to it is underway now. A silent, inexorable shift in the star that gives us life. This understanding deepens our appreciation for the present moment and the stable conditions we enjoy. It is a powerful demonstration of the laws of physics in action, a cosmic lesson in change and impermanence. The Sun's journey to becoming a red giant is not a future event. It is a path it is already walking, and we are along for the ride, living in a brief, golden age of stability between the star's fiery youth and its expansive old age. Recognizing this continuity is key to grasping our place in the cosmos, a fleeting moment in the long, evolving story of a star. The fate of Earth is the most personal and dramatic part of this story, but the Sun's transformation will reshape the entire solar system, with each planet and celestial body meeting a unique and violent end dictated by its distance from the evolving star. The journey of destruction begins with the innermost world, Mercury. This small, rocky planet will be the first to be consumed, vaporized almost instantaneously as the Sun's photosphere expands past its orbit. The process for Venus is similar. Its thick carbon dioxide atmosphere will offer no protection against the stellar inferno, and it too will be swallowed whole, its material added to the Sun's outer layers. The asteroid belt, located between Mars and Jupiter, will be scoured clean. Some asteroids will be vaporized, while others will be flung into chaotic new orbits or ejected from the solar system entirely by the gravitational perturbations of the swelling Sun and the migrating giant planets. The increasing luminosity of the Sun during its red giant phases will have drastic effects even before physical engulfment occurs. For Mars, the situation is complex. While its orbit may place it just outside the maximum predicted radius of the red giant Sun, the planet will be rendered utterly uninhabitable. Any remaining water ice or thin atmospheric gases will be boiled away and stripped by the intense solar wind. The surface will be baked, and any potential for future habitability will be permanently erased. The real dynamical chaos, however, will occur in the realm of the gas giants. As the Sun loses a significant portion of its mass through the powerful stellar winds of the red giant and asymptotic giant branch phases, its gravitational grip on the outer solar system will weaken, according to the laws of orbital mechanics. A decrease in the central mass causes the remaining planets to spiral outward. Jupiter, Saturn, Dot, Uranus, and Neptune will all migrate to wider orbits. This sounds like a reprieve, but it introduces new instabilities. Their new orbital paths could become chaotic, potentially leading to close encounters and even collisions between these giants. Or they could be gravitationally ejected from the solar system altogether to become rogue planets drifting in interstellar space. The moons of these gas giants will face their own apocalyptic trials. Worlds like Jupiter's Europa and Saturn's Enceladus, which currently harbour subsurface oceans, will see those layers of ice and water melt and then boil away into space as the sun's intensity grows. Icy moons like Callisto and Ganymede will have their surfaces completely remodelled. The dramatic rings of Saturn, composed of countless ice particles, will sublimate, turning directly from solid to gas, vanishing forever under the sun's increased heat. For a time, during the peak of the sun's luminosity, these outer planetary systems might briefly become warmer, but this is a fleeting and destructive warmth, not a nurturing one. The Kuiper Belt, the region of icy bodies beyond Neptune, will also be transformed. Objects like Pluto will see their surface ices of nitrogen, methane, DOT, and carbon monoxide sublimate, creating temporary, tenuous atmospheres that are quickly lost to space. The entire structure of this distant belt will be disrupted by the sun's mass loss and the outward migration of the giant planets, scattering many of these objects. The Oort cloud, the vast spherical shell of icy planetesimals at the solar system's extreme frontier, will also feel the sun's weakening gravity. Many of these cometary nuclei will be set adrift, becoming free-floating objects between the stars. The entire architecture of our planetary system, stable for billions of years, will be torn apart. The asteroid belt is gone. The inner planets are consumed. The gas giants are unmoored and wandering, and the icy reservoirs are dissipated. What remains after the planetary nebula phase is a vastly different system. A central white dwarf star orbited by a potential debris disk of shattered asteroids and comets, and possibly a few scorched, barren giant planets in distant, silent orbits. These surviving planets would be cold, dark worlds, their atmospheres likely stripped, their moons gone. They would bear no resemblance to the vibrant worlds we know today. This comprehensive demolition of the solar system highlights the profound interconnectedness of all its parts. A change in the star inevitably cascades through every orbiting body, from the smallest rock to the largest planet. The same physics that governs the fusion in the sun's core also governs the orbital dynamics of Pluto and the sublimation of a comet's ice. It is a system-wide cataclysm, a complete reset that erases the current solar system and leaves behind only a faint, fossilized remnant. This broader perspective makes the story of the sun's death not just about the end of Earth, but about the end of a complete cosmic neighborhood, a testament to the fact that stars are the anchors of their planetary systems, and when the anchor changes, everything else must change with it, often with violent and irreversible consequences. Observing other white dwarf systems provides evidence for this chaotic reshuffling, as we see the chemical signatures of accreted planetary debris in their spectra, telling a story of destruction that happened long ago around other stars. So, the solar system's fate is a chain reaction of destruction, starting with the innermost worlds and propagating outward, leaving nothing untouched. It is a reminder that our entire cosmic address is temporary, a configuration that exists for a time but is destined to be dissolved and rearranged by the relentless evolution of its central star. With the solar system now a ghost of its former self, its planets scattered or consumed, and its central star a cooling white dwarf. We must widen our gaze to the cosmic scale to understand the ultimate context of this transformation. The death of the Sun is not an isolated event, but part of a grand narrative that encompasses every star in every galaxy. A story written in the laws of physics and unfolding over timescales that dwarf human history. The universe, currently about 13.8 billion years old, is in its stellar heyday, with billions of galaxies each containing billions of stars actively shining and forming new generations. This period of abundant light and energy began hundreds of millions of years after the Big Bang, when the first stars ignited, ending the cosmic dark ages. These primordial stars were massive and short-lived, exploding as supernovae and seeding the cosmos with the first heavy elements. Subsequent generations of stars, including our Sun, formed from this enriched material, allowing for the creation of planets and the potential for life. However, this era of light and life is transient. The process of star formation is gradually slowing down as the raw materials, hydrogen and helium gas, are used up in the creation of stars and are not replenished. In the Milky Way and other galaxies, the rate of star formation has already peaked and will continue to decline over the next several billion years. As the Sun cools into a black dwarf, the galaxy around it is also aging. The merger with the Andromeda Galaxy, expected in about 4 billion years, will trigger a final burst of star formation, but after that, the combined galaxy, often called Milkomeda, will slowly redden and dim as its massive stars die off and only longer-lived, lower-mass stars remain. Red dwarf stars, with masses a fraction of the Sun's, can burn for trillions of years, but even they will eventually exhaust their fuel. When the last red dwarf flickers out, the universe enters what astronomers call the degenerate era. This period is dominated by the remnants of stars, white dwarfs, neutron stars, and black holes. White dwarfs, like the Sun's corpse, will continue to cool, radiating away their residual heat until they become black dwarfs, cold. Dark spheres of carbon and oxygen that emit no light. Neutron stars dot, the incredibly dense cores left after supernova explosions, will also cool and spin down, their magnetic fields weakening over time. Black holes, from stellar mass to supermassive, will be the last significant entities, but they too are not eternal. Stephen Hawking theorized that black holes slowly lose mass through quantum effects, emitting radiation now known as Hawking radiation. For a black hole with the mass of the Sun, this evaporation process would take an unimaginably long time, around 10 to the 67 years. For the supermassive black holes at the centers of galaxies, with masses millions or billions of times that of the Sun, the evaporation time scales to 10 to the 100 years or more. During these eons, the universe continues to expand, driven by dark energy. Galaxies beyond our local group will be pushed away by the accelerating expansion. Their light red-shifted until they are no longer observable. The cosmos becomes a collection of isolated galaxy clusters, then individual galaxies, and finally, even stars within galaxies become invisible to each other. The temperature of the universe approaches absolute zero, and the entropy, or disorder, reaches its maximum. In this state, known as the heat death of the universe, no energy gradients exist, meaning no work can be done, and no new structures can form. It is a uniform, cold, and dark cosmos. The atoms that once made up stars, planets, and life are spread so thin that they rarely interact. If proton decay is a real phenomenon, as predicted by some grand unified theories, then even the matter in white dwarfs and neutron stars will eventually decay into radiation, leaving behind a sea of photons and leptons. The legacy of the Sun and all stars is the enrichment of the universe with heavy elements, which made possible the formation of rocky planets and the chemistry of life. But in the heat death, this legacy fades into the background radiation of the cosmos for humanity, or any civilization that arises. This cosmic future is a profound reminder of the impermanence of all things. Yet, it also highlights the incredible privilege of existing in a time when the universe is vibrant and explorable. Our ability to understand these distant futures is a testament to human curiosity and the power of science. It motivates us to protect our fragile world and to reach for the stars, not just for survival, but for the sake of knowledge and wonder. The story of the Sun's death thus connects to the largest questions about the nature of time, existence, and our place in the cosmos, encouraging us to make the most of the light while it lasts. The timeline from the present to the heat death is so vast that it is often divided into cosmological eras. The Stelliferous era, where we are now, is characterized by active stars. This will be followed by the Degenerate era, then the Black Hole era, and finally the Dark era, where no macroscopic objects exist. Throughout this, the constant is the increase in entropy, a measure of disorder that always rises in isolated systems like the universe. This inevitable trend toward equilibrium is what drives the heat death. For civilizations, this means that the window for activity is finite, urging us to act now to explore and learn. In the Degenerate era, the occasional collision between brown dwarfs or white dwarfs might trigger brief flashes of light, but these events are rare and do not halt the overall cooling. Planets that may still orbit white dwarfs will be frozen and dead, with no atmosphere or liquid water. Any remaining life would have long since perished. The black hole era sees the dominance of these gravitational giants, but even they are not permanent. As black holes evaporate, they emit particles and radiation, slowly diminishing in mass until they vanish in a final burst of energy. After the last black hole disappears, the universe enters the dark era, where only elementary particles and radiation remain, spread uniformly across an ever-expanding space. The concept of time itself may become meaningless in this state, as no processes occur to mark its passage. This cosmic story is not just a prediction, but is based on rigorous observational evidence and theoretical models. Scientists study the cosmic microwave background, the afterglow of the Big Bang, to understand the universe's initial conditions. They observe distant supernovae to measure the acceleration of expansion driven by dark energy. They simulate stellar evolution on supercomputers to verify the fate of stars like the Sun. All these lines of evidence point to the same conclusion. The universe is evolving toward a cold, dark end. However, this does not diminish the significance of our current era. We live in a special time when the universe is full of light, diversity, and potential. The elements forged in stars have come together to form our world and us, allowing us to contemplate the cosmos. This self-awareness is a rare and precious gift in the grand scheme of things. While the heat death seems bleak, it is a natural consequence of the laws that also allow for complexity and life. Understanding this broader context gives meaning to our efforts to explore space, preserve our planet, and advance knowledge. It inspires a sense of wonder and responsibility, knowing that we are part of a vast, evolving cosmos. The death of the Sun is a single chapter in this story, reminding us that everything changes, but also that we have the opportunity to learn, grow, and appreciate the beauty of the universe while it lasts. So, as we look up at the night sky, we see not just stars, but the past and future of everything, connected through the relentless flow of time and the unwavering rules of physics, while the cosmic scale of the sun's demise reveals a universe destined for cold and darkness. This knowledge brings us back to a very human scale question. What does this mean for us? And what can we do about it? The certainty of Earth's eventual destruction is not a reason for despair, but a powerful catalyst for action, driving the most ambitious project imaginable, the journey to become an interstellar species. This is not science fiction. It is a logical and necessary response to a foreseeable natural disaster on a planetary scale. The timeline, while immense, provides a clear deadline. We have approximately 1 billion years before the sun's increasing luminosity makes Earth uninhabitable, and about 7.5 billion years before physical engulfment. These are not short timeframes, but they are finite, and the technological and societal challenges of leaving our solar system are so profound that they demand we start thinking about them now. The first step is mastering our own solar system, establishing permanent, self-sustaining habitats on Mars or perhaps on the moons of Jupiter and Saturn would serve as crucial stepping stones. These outposts would allow us to develop and test the technologies needed for long-duration spaceflight, closed-loop life support systems, and resource utilization in harsh environments, learning to live on Mars, with its thin atmosphere and lack of a magnetic field, is a dress rehearsal for living on a world orbiting another star. The next step is the monumental leap to another star system. The nearest star, Proxima Centauri, is about 4.24 light-years away, with current propulsion technology. A journey there would take tens of thousands of years, which is utterly impractical. This means we need revolutionary advances in propulsion, concepts like nuclear fusion rockets, which could theoretically reach speeds of up to 10% the speed of light, are actively being researched. Even more speculative are technologies like light sails propelled by powerful lasers, or matter-antimatter annihilation engines. These could potentially reduce travel times to within a human lifetime. The challenges are not just technological, they are also biological. How does the human body cope with years of weightlessness and exposure to cosmic radiation? We would need to develop artificial gravity, perhaps through rotating habitats, and advanced shielding. Alternatively, we might send frozen embryos or genetic material, with automated systems raising a new generation upon arrival, a concept that raises profound ethical questions. Another possibility is the concept of a generation ship, a massive vessel that sustains a population for centuries during the voyage. This would require a completely self-contained ecosystem, recycling all air, water, and waste, and maintaining social stability over generations. The psychological and societal hurdles are immense. Then there is the challenge of what we find when we arrive. The discovery of exoplanets has revealed thousands of worlds orbiting other stars. Some, like those in the habitable zone of red dwarf stars, could potentially host life or be terraformed for human habitation. However, potentially habitable does not mean Earth-like. A planet like Proxima Centauri b orbits very close to its dim star, likely resulting in tidal locking, where one side is perpetually scorched and the other frozen. Adapting to such an environment would be incredibly difficult. Terraforming, the process of altering a planet's environment to make it Earth-like, is a concept that would require centuries or millennia and energy resources far beyond our current capabilities. It might involve melting ice caps to release water, introducing genetically engineered microbes to produce oxygen, and building magnetic shields to protect against stellar radiation. The more feasible near-term goal might be to construct massive orbital habitats, like O'Neill cylinders, which could house millions of people in a controlled environment, independent of any planet. These could be placed in stable orbits around stable stars, creating a network of human colonies across the galaxy. This endeavour would require unprecedented international cooperation and a long-term vision that transcends generations. It cannot be the project of a single nation or corporation. It must be a global human enterprise. The resources required would be astronomical, necessitating the mining of asteroids and moons for materials. The development of a space-based economy is therefore a prerequisite. The knowledge that Earth has an expiration date should motivate us to invest in science, technology, engineering, and mathematics education, fostering the innovators who will solve these problems. It also raises questions about who gets to go. Would it be a select few, or would we strive to preserve the genetic and cultural diversity of humanity? This leads to deeper ethical considerations about our responsibility to other life on Earth. Should we attempt to bring other species with us? Creating biosphere arcs to preserve Earth's biodiversity would be a complex but noble goal. Furthermore, the search for a new home is intertwined with the search for extraterrestrial intelligence. If other civilizations have faced similar existential threats, they might have left behind artifacts or signals that could guide us. The study of astrobiology is crucial. Understanding how life arises and survives in extreme environments on Earth helps us identify what to look for on other worlds. While the physical challenges are daunting, the greatest obstacle may be maintaining the will and focus over centuries. Human history is marked by short-term thinking and conflict. To undertake a project that spans millennia, we need to cultivate a new perspective, one that values the future of our species as much as the present. This means creating cultural narratives, stories, and institutions that are dedicated to the long-term survival and flourishing of humanity beyond Earth. The clock is ticking, but it is ticking slowly. We have time to prepare, but we must start now. Every rocket launch, every discovery of a new exoplanet, every advance in artificial intelligence or biotechnology is a step toward this ultimate goal. The death of the sun, therefore, is not just an end. It is a beginning. It is the reason we must look to the stars, not with fear, but with hope and determination. It unites us in a common purpose, to ensure that the story of humanity does not end with the star that gave us life. This mission gives meaning to our scientific endeavours and inspires us to achieve what might seem impossible today. So, while the sun will eventually die, the legacy of humanity could live on, scattered among the stars, a testament to a species that looked into the future and dared to reach for it. The profound implications of the sun's eventual death extend far beyond the realm of astrophysics, forcing us to confront fundamental questions about meaning, legacy, and our place in a universe governed by impermanence. This knowledge acts as a powerful lens through which we can examine our priorities, our values, and the very purpose of our brief, brilliant moment in the cosmic spotlight. The certainty that Earth, and all human achievement upon it, will one day be vaporized can initially seem nihilistic, a verdict of ultimate pointlessness. However, this perspective can be inverted to become a source of profound clarity and motivation. If nothing is permanent, then the value of our actions is not derived from their eternal endurance but from their quality and impact in the present. The transience of our world does not rob our lives of meaning, it concentrates it. The love we share, the knowledge we create, the art we produce, the connections we forge, these things matter not because they will last forever, but because they are beautiful and significant now. The finite nature of our civilization challenges the traditional concept of legacy. We often strive to build things that last, to leave a mark that endures for centuries. The sun's fate tells us that on a long enough timeline, all physical monuments, every city, every monument, every digital record will be erased. This shifts the focus of legacy from the material to the immaterial. Our true legacy may not be in stone or steel, but in the ideas we propagate, the scientific understanding we advance, and the cultural and ethical progress we achieve. The knowledge we gather about the universe, the stories we tell, the moral frameworks we develop. These are the things that could potentially be carried forward by future generations, whether they remain on Earth or journey to the stars. This perspective fosters a deep sense of responsibility toward the present, understanding that our time is limited, both individually and as a species, can be a powerful antidote to procrastination and trivial conflict. It urges us to resolve our differences, to address pressing global issues like climate change and inequality, and to channel our collective energies toward growth and exploration. The potential destruction of our world in 1 billion years does not diminish the urgency of saving it today. In fact, it highlights the incredible rarity and preciousness of the stable, life-giving conditions we currently enjoy. It argues for stewardship, for protecting this pale blue dot, not as a permanent possession, but as a cherished and temporary home that must be nurtured for all who inhabit it now and in the immediate future. On a philosophical level, the sun's life cycle is a grand lesson in non-attachment. It teaches us that change is the only constant, from the microscopic scale of our own cells to the macroscopic scale of galaxies. Embracing this reality, rather than resisting it, can lead to a more peaceful and resilient existence. It encourages us to appreciate the present moment without clinging to it, to find joy in the fleeting beauty of a sunset, knowing that the star creating it is itself in a state of constant flux. This cosmic context can also cultivate a profound sense of humility. We are not the center of the universe. We are a transient phenomenon on a speck of dust orbiting an average star in an unremarkable galaxy. This realization can dissolve ego and anthropocentrism, replacing them with a sense of wonder at our ability to comprehend such vast and ancient processes. We are the universe become self-aware, a way for the cosmos to understand itself. Our quest for knowledge, our drive to explore, and our capacity for awe are themselves meaningful outcomes of cosmic evolution. The narrative of the sun's death also reframes our relationship with time. Human history spans mere thousands of years, a blink in the life of a star. Contemplating billions of years stretches our minds and forces us to think in terms of deep time. This long-term perspective is essential for tackling challenges that span generations. It asks us to make decisions not for the next election cycle, but for the next millennium, fostering an intergenerational solidarity that is often lacking in modern society. Ultimately, the philosophical response to this cosmic forecast is not one of despair but of liberated purpose. The knowledge that the stage will eventually be dismantled liberates us to play our parts with more passion, compassion, and creativity. It tells us that what we do matters precisely because it is temporary. Our efforts to alleviate suffering, to create beauty, to understand the universe, and to build a better future are valuable not in spite of their impermanence, but because of it. They are our unique and irreplaceable contribution to the brief flicker of consciousness in a vast and mostly silent cosmos. The death of the sun, therefore, is not just an astronomical event. It is a mirror held up to humanity, asking us what we will do with the time we have. It challenges us to live intentionally, to love deeply, and to strive for a legacy of wisdom and kindness that, even if it doesn't last forever, makes the universe a slightly more enlightened place for our having been here. This is the ultimate meaning we can derive from the stars. Our time is limited, so let us make it count. The story of our sun's fate is not unique. It is a common narrative shared by the vast majority of stars in the universe. Yet the specific details of a star's life and death are exquisitely sensitive to its initial mass. Comparing the sun to its stellar siblings reveals a fascinating spectrum of destinies, from the quiet fade of the smallest red dwarfs to the spectacular explosions of the most massive giants. Our sun is a G-type main sequence star, a fairly average, middle-of-the-road star in terms of mass, temperature, and luminosity. This places it in the most common category for stars that host planets potentially capable of supporting life as we know it. Its predicted journey from main sequence star to red giant to white dwarf is the standard pathway for stars with masses between roughly 80% and 8 times the mass of the Sun. However, stars with lower and higher masses follow dramatically different evolutionary tracks. Consider the humble red dwarf, or M-type star. These are the most numerous stars in the galaxy, making up about 75% of all stars. They are much less massive than the Sun, often having only 10 to 50% of the Sun's mass. Because of their lower mass, the pressure and temperature in their cores are much lower, causing them to fuse hydrogen at a far more leisurely and efficient rate. This incredible fuel efficiency grants them astonishingly long lifespans. A typical red dwarf can remain on the main sequence for trillions of years, far longer than the current age of the universe. Their lives are so long that not a single red dwarf has ever died of old age in the cosmos. The universe simply hasn't been around long enough. When they do eventually deplete their hydrogen, they are believed to slowly heat up as they contract, eventually becoming blue dwarfs before fading directly into white dwarfs without ever going through a dramatic red giant phase. They simply lack the mass to initiate the shell burning that causes significant expansion. Planets orbiting red dwarfs face challenges like tidal locking and intense stellar flares, but their stellar hosts provide stability for time spans that dwarf the Sun's entire existence. On the opposite end of the spectrum are the massive stars, the O and B types. These stellar behemoths can be 8, 10, or even over 100 times more massive than the Sun. They live fast and die young. Their immense gravity creates crushing pressures and temperatures in their cores, driving fusion reactions at a ferocious rate. They burn through their hydrogen fuel in just a few million years, a blink of an eye compared to the Sun's 10 billion year main sequence life. Their evolution after hydrogen exhaustion is a frantic race against gravity. They undergo successive stages of fusion, creating concentric shells of elements like helium, carbon, dot, neon, oxygen, and silicon, all surrounding an iron core. Unlike the Sun, which cannot fuse elements beyond carbon and oxygen, these massive stars have the power to forge all the elements up to iron in their cores. The creation of an iron core is the star's death knell. Iron fusion consumes rather than releases energy, and without this energy output to support the core against gravity, it collapses catastrophically in a matter of seconds. This collapse triggers a titanic rebound explosion known as a core collapse supernova, an event so energetic that it can outshine an entire galaxy for a brief period. The supernova scatters the newly forged heavy elements throughout space and leaves behind an incredibly dense remnant. If the collapsing core is between about 1.4 and 3 solar masses, it forms a neutron star, a city-sized object so dense that a teaspoon of its material would weigh billions of tons. If the core is more than about 3 solar masses, the collapse is unstoppable, and it forms a black hole. So, while the Sun will end its life by gently puffing off its outer layers and leaving a white dwarf. A massive star ends in a violent supernova that seeds the galaxy with the elements necessary for planets and life. There is also an intermediate case. Some stars, with initial masses up to about 8 times that of the Sun, may still end their lives in a different kind of supernova. If a white dwarf in a binary system accretes enough material from its companion to push it over the Chandrasekhar limit of about 1.4 solar masses, it can undergo a runaway carbon fusion reaction that completely obliterates the star in a Type Ia supernova. These events are crucial cosmic yardsticks for measuring distances in the universe. The diversity of stellar deaths highlights a fundamental cosmic truth. Mass is destiny. The initial mass of a star determines its internal pressure, its temperature, its fusion rate, its lifespan, and the manner of its death. Our Sun sits in a relatively calm and long-lived middle ground. It is not so small that it denies its planets the energy for a rapid development of life. Nor is it so massive that it dies before life has a chance to evolve beyond the most primitive stages. This comparison puts our solar system's future into a broader context. The quiet fade of a red dwarf, the violent explosion of a massive star, and the transformative expansion of a star like the Sun are all part of the rich tapestry of stellar evolution. Each path plays a crucial role in the cosmic cycle. The long-lived red dwarfs provide stable homes for potentially immense spans of time. The massive stars, though short-lived, are the universe's primary factories for heavy elements. And stars like our Sun, in their red giant death throes, contribute significantly to the carbon and nitrogen content of the galaxy. When we look at the night sky, we are seeing stars at every point along these evolutionary paths. The red giant Betelgeuse shows us a future that is more massive and explosive than our Sun's. The white dwarf Sirius B shows us our Sun's ultimate fate, and the countless faint red dwarfs, invisible to the naked eye, represent the most common and enduring stellar objects in the cosmos. Understanding these comparisons allows us to appreciate our Sun not as a solitary object, but as one representative of a vast and varied stellar population, each member following a path dictated by the simple, yet powerful, parameter of its birth mass, the magnificent planetary nebula phase, while brief, represents one of the most visually stunning and scientifically informative periods in the death of a star like the Sun. This phase is the mechanism by which the star gracefully and violently returns a significant portion of its mass to the cosmos, enriching the galactic environment with newly forged elements. The process begins in earnest after the star has passed through its red giant phases on the asymptotic giant branch. At this stage, the star is a cosmic onion, with a core of inert carbon and oxygen, a shell where helium is fusing into carbon, and an outer shell where hydrogen is fusing into helium. This configuration is highly unstable. The star undergoes thermal pulses, periodic and violent bursts of energy from the helium-burning shell that push the outer envelope even further out. These pulses, combined with the intense radiation pressure from the hot core, drive a powerful stellar wind that begins to eject the star's outer layers into space. This mass loss is catastrophic. The star can shed up to half of its entire mass over a period of 100,000 years. The ejected material forms a vast, expanding shell of gas and dust surrounding the central star. At this point, the core is still hidden beneath the escaping envelope. However, as the ejection continues, the deeper, hotter layers of the star are exposed. The core, no longer supported by fusion, is contracting and heating up, and it is on its way to becoming a white dwarf when the final layers of the envelope are blown away. The hot, dense core is laid bare. Its surface temperature skyrockets to 100,000 degrees Celsius or more, and it begins emitting immense amounts of ultraviolet radiation. This intense UV light floods the surrounding cloud of ejected gas, which is now moving outward at speeds of tens of kilometers per second. The ultraviolet photons from the central star are so energetic that they rip electrons away from the atoms in the gas cloud, a process called ionization, when these free electrons eventually recombine with the ionized atoms. They fall back into their stable orbits, releasing energy in the form of light. Each chemical element emits light at specific, characteristic wavelengths, causing the gas to glow in vibrant, distinct colours. Oxygen, for instance, often glows a characteristic greenish blue, while hydrogen emits a strong red light, and nitrogen contributes shades of purple and crimson. This is what creates the beautiful, colourful structures we see in images from telescopes like the Hubble Space Telescope. The name planetary nebula is a historical misnomer from the 18th century, when astronomers like William Herschel observed their often round, planet-like shapes through small telescopes. They have absolutely nothing to do with planets. The morphology of planetary nebulae is incredibly diverse. While some are roughly spherical, many exhibit complex bipolar, elliptical, dot, or even intricate butterfly-like shapes. The shaping mechanisms are an active area of research, but they are thought to be influenced by several factors. If the central star is part of a binary system, the companion star can gravitationally funnel the ejected material into lobes or disks. Strong magnetic fields from the central star can also channel the outflowing gas. Additionally, the rotation of the progenitor star and the manner of the mass loss itself can create asymmetries. The entire nebula continues to expand and will eventually disperse into the interstellar medium over a period of 20,000 to 50,000 years, a mere blink in astronomical time. During this brief window, the planetary nebula is a crucial source of chemical enrichment. The ejected material is not pure hydrogen and helium. It is heavily laced with elements processed in the star's interior. This includes carbon, nitrogen, and oxygen, as well as S-process elements like strontium and barium, which are created by slow neutron capture during the thermal pulses. By expelling this material, stars like the Sun are the primary sources of carbon and nitrogen in the universe, elements essential for life as we know it. For astronomers, planetary nebulae are invaluable cosmic laboratories. Their spectra reveal their chemical composition, density, and temperature. By studying their expansion velocities and sizes, we can estimate their ages and distances. They also serve as probes of the chemical evolution of galaxies, as their composition reflects the enrichment history of their birthplace. The central white dwarf, now exposed, begins its long cooling journey. Initially, it is one of the hottest objects in the universe, but with no fusion to sustain it. It will slowly dim over billions of years. The study of these central stars helps us understand the final stages of stellar evolution and the physics of white dwarfs. The entire planetary nebula phase is a beautiful demonstration of the cycle of matter in the galaxy. The material that was once part of the star is now returned to space, where it will mix with other gas and dust. In millions or billions of years, this enriched material will collapse under gravity to form new stars, new planets, and perhaps even new life. The Sun will one day create its own planetary nebula, a final, brilliant farewell before settling down into a long, quiet retirement as a white dwarf. This phase is not an end, but a transformation, a recycling of stellar material that ensures the continued chemical evolution and vibrancy of the Milky Way galaxy. It is a powerful reminder that even in death, A star gives birth to the potential for new beginnings. The brilliant but fleeting planetary nebula phase culminates in the revelation of the star's core, now a white dwarf, which will serve as the long-lasting tombstone for our solar system. This Earth-sized remnant is phenomenally dense, packing roughly half the mass of the original Sun into a volume 1,000,000 times smaller. A single teaspoon of its material would weigh many tons on Earth. This incredible density is not supported by the thermal pressure of fusion, as in a normal star, but by a quantum mechanical effect known as electron degeneracy pressure. When matter is compressed to this extreme, electrons are forced into a very high energy state, and they resist further compression with tremendous force. This pressure is independent of temperature, which is a key feature that dictates the white dwarf's future. The newborn white dwarf is searingly hot, with surface temperatures that can exceed 100,000 degrees Celsius. But this heat is merely residual, left over from its earlier fusion-powered life, with no internal energy source. Its only fate is to cool down by radiating this heat away into the cold vacuum of space. The cooling process is rapid at first. Over the first 100 million years, the white dwarf will lose heat quickly, its temperature plummeting and its colour shifting from brilliant white to yellow. Its luminosity, which was initially quite high, will drop dramatically after about 1 billion years. It will have cooled to a temperature of around 10,000 degrees, and after 10 billion years, it might be down to a few thousand degrees, appearing as a dim red object. The rate of cooling slows down considerably over time because as the object gets cooler, it has less thermal energy to radiate per second. The ultimate theoretical endpoint of this cooling is a black dwarf, a cold dot, dark stellar crystal that has reached thermal equilibrium with the cosmic background radiation and emits no detectable light. However, the universe is only about 13.8 billion years old, which is not nearly long enough for even the first white dwarfs to have cooled to this state. The Sun's white dwarf will require many times the current age of the universe to become a black dwarf, a testament to the immense residual heat it contains. During this immensely long cooling phase, the internal structure of the white dwarf undergoes a fascinating change. As the temperature drops sufficiently, the carbon and oxygen ions within it begin to arrange themselves into a crystalline lattice, effectively turning the entire core into a planet-sized diamond. This crystallization process releases latent heat, which can temporarily slow the cooling process, providing a small delay in the star's final fade to black. The surface of the white dwarf is typically composed of the lightest elements, hydrogen and helium, which float to the top. However, the atmospheres of many white dwarfs are observed to be polluted with heavier elements like silicon, iron, and oxygen. This is compelling evidence for the enduring presence of planetary systems. Asteroids and comets that survived the red giant phases can be perturbed by the migrating giant planets, sending them on trajectories that bring them close to the white dwarf. The intense tidal forces from the dwarf's powerful gravity can rip these rocky bodies apart, creating a debris disk of dust and gas that slowly spirals inward and accretes onto the star's surface, imprinting its chemical signature there for the solar system. The white dwarf era is one of profound darkness and cold. Any surviving outer planets, like Jupiter and Saturn, will orbit this faint ember in wide, silent orbits. Their surfaces and atmospheres will be frozen solid, with no internal heat source or stellar energy to sustain geological or atmospheric processes. The once vibrant gas giants will become dark, barren worlds. The habitable zone, the region where liquid water could exist, will have shrunk to a point virtually at the surface of the white dwarf itself. The astronomical study of white dwarfs provides crucial information about the ultimate fate of stars and the chemistry of planetary systems. By analysing their spectra, astronomers can determine their composition, temperature, and cooling age. The coolest white dwarfs in a star cluster act as cosmic clocks, providing a lower limit for the cluster's age, which in turn helps date the galaxy itself. The long-term stability of white dwarfs is remarkable. They will persist for trillions of years, far outliving all remaining main sequence stars except the lowest mass red dwarfs, their eventual fate. Over timescales so vast they challenge comprehension. Depends on the stability of the proton. If protons are unstable and decay, as suggested by some grand unified theories, then the white dwarf will very slowly evaporate over perhaps 10 to the 34 years. If protons are stable, then the white dwarf will simply continue to cool indefinitely, eventually becoming a black dwarf. The white dwarf phase represents the final, stable form of ordinary matter for the vast majority of stars in the universe. It is the end product of stellar evolution for stars like our Sun, a quiet and dark conclusion to a life that began in a brilliant collapse of gas and dust. The transformation from a shining star to a cold crystal is the last step in the journey, a slow and silent fade that stands in stark contrast to the violent and dramatic phases that preceded it. It is a reminder that even the most energetic processes in the universe ultimately give way to equilibrium and silence, as the laws of thermodynamics dictate the final state of all things. For our solar system, the white dwarf sun is the final chapter, a cold, dark monument to the star that once gave light and life to Earth. As the white dwarf sun continues its slow fade into darkness, the final chapter of its story merges with the ultimate destiny of the cosmos itself, a journey toward an era of perpetual cold and silence. This white dwarf, once the brilliant core of our star, is now a cooling ember, radiating its residual heat into the void. Over billions of years, its temperature will drop from thousands of degrees to just a few degrees above absolute zero. During this immense timescale, the universe around it is undergoing its own profound transformation. The era of stars, known as the Stelliferous Era, is drawing to a close. Star formation has already peaked and is in decline across galaxies as interstellar gas is depleted. The Milky Way, having merged with Andromeda to form Milkomeda, now contains mostly aging stars, red dwarfs that will shine for trillions of years. But eventually, they too will exhaust their fuel. As these long-lived stars die, the universe enters the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. The white dwarf sun is one among countless such objects, all cooling in unison. Their light, once a beacon of energy, dims until it is indistinguishable from the background. In this era, the planets that may still orbit these remnants are frozen wastelands, their orbits stable but devoid of activity. The outer planets of our solar system, like Jupiter and Saturn, have drifted further out due to the sun's mass loss, but they are now dark and cold, their atmospheres frozen solid, and any geological processes long since halted. The asteroid belts and Kuiper belt objects are silent, their materials scattered or inert. As time progresses, the expansion of the universe, driven by dark energy, accelerates. Galaxies beyond the local group recede faster than light, their images red-shifting into oblivion until they are no longer visible. The cosmos becomes a collection of isolated galaxy clusters, then individual galaxies, and finally, even stars within those galaxies become invisible to one another. The universe is growing darker and more lonely, on timescales of quadrillions of years. The degenerate era gives way to the black hole era during this period. Black holes are the primary sources of energy, but they are not eternal. Through Hawking radiation, black holes slowly evaporate. A stellar mass black hole might take 10 to the 67 years to vanish, while supermassive black holes at galactic centers could persist for 10 to the 100 years. As they evaporate, they emit particles and radiation, providing fleeting flashes of light in an otherwise dark cosmos. However, these events are rare and do little to offset the overall cooling. After the last black hole dissipates, the universe enters the dark era. In this final state, only elementary particles and radiation remain, spread uniformly across an ever-expanding space. The temperature approaches absolute zero universally, and no energy gradients exist to perform work. This is the heat death of the universe, a state of maximum entropy where no new structures can form and no processes occur. The atoms that once made up stars, planets, and life are now so diffuse that interactions are virtually non-existent. The concept of time itself may become meaningless, as there are no events to mark its passage. For the white dwarf sun, this means a slow crystallization of its carbon-oxygen core into a diamond-like structure, but even this process is completed long before the heat death. It will become a black dwarf, a cold, dark sphere that emits no light. However, the universe is not old enough for any black dwarf to exist yet. It will take many times its current age for the sun's remnant to reach this state. Throughout these eons, the legacy of the sun's material persists, but in a form that is increasingly irrelevant. The elements it forged, carbon, oxygen, nitrogen, were scattered during the planetary nebula phase and have been incorporated into new generations of stars and planets. But in the dark era, even these elements are diluted into a thin haze. The cycle of stellar birth and death, which enriched the galaxy for billions of years, has ceased. The universe is silent, dark, and uniform. This ultimate fate is not a sudden event, but a gradual winding down, dictated by the laws of thermodynamics. Entropy, a measure of disorder, increases until it reaches a maximum, and the universe achieves thermal equilibrium. From a human perspective, this outcome might seem bleak, but it is a natural consequence of the same physical laws that allowed for the emergence of complexity and life. Our ability to comprehend this journey is a testament to the remarkable capacity of intelligence to understand the cosmos. While the light of the sun and all stars will eventually fade, the knowledge we gain about the universe gives meaning to our existence. It inspires us to cherish the present, to explore, and to strive for a legacy that transcends our physical limitations. In the end, the silence and darkness are not to be feared but understood as part of the grand tapestry of cosmic evolution, a reminder that we are part of something vast, dynamic, and beautiful, even in its final, quiet state.